Imagine staring into the vastness of space, expecting to see the usual galaxies shaped like elegant spirals, glowing in shades of blue and white, their young stars burning brightly. But then, something strange appears. A spiral galaxy, just like the others in shape, but instead of the expected colors, it's drenched in red. That's not how things are supposed to work. Spiral galaxies are young and full of star-forming regions, and those regions should shine in blue. Red galaxies, on the other hand, are usually elliptical, old, inactive, and no longer forming new stars. So why do these red spirals exist? Why do they break the rules of everything we thought we understood about galactic evolution? Scientists have been asking the same thing, and the answers are still a mystery. To understand why red spiral galaxies are so unusual, we need to break down what makes a galaxy red or blue in the first place. It all comes down to star formation. When a galaxy is actively forming stars, the youngest and hottest stars shine in blue. These stars burn quickly, lasting only a few million years before exploding as supernovae. In contrast, red stars are cooler and much older. If a galaxy appears red overall, it usually means that the hot blue stars have long since burned out, leaving behind only the older, cooler ones. This is exactly what we see in elliptical galaxies, giant clouds of stars with no ongoing star formation. But spiral galaxies are different. Their swirling arms are full of gas and dust, the essential ingredients for making new stars. So, in theory, spirals should always be blue, because they should always be forming new stars. And yet, these red spirals exist, defying everything we thought we knew. Astronomers first started noticing these red spirals when surveying the sky in large numbers. Before that, galaxies were mostly classified based on a simple rule: spirals are blue, ellipticals are red. But as telescopes became more powerful and data collection expanded, researchers started seeing more and more of these strange galaxies. They had all the clear structure of spirals, arms winding around a bright center, dust lanes snaking through the stars. But instead of shining in blue light, they glowed in red. This wasn't just a rare fluke either. As data from large sky surveys, like the Sloan Digital Sky Survey, came in, scientists realized that red spirals weren't just a few outliers. There were enough of them to suggest that something important was happening, something that could change our entire understanding of how galaxies evolve. One of the leading theories about red spirals is that they used to be normal, star-forming galaxies, but somehow had their star formation shut off. This process, known as quenching, is something astronomers have observed in many galaxies, but it usually happens in ellipticals. When a galaxy is quenched, it means something has stopped the gas in its arms from forming new stars. There are a few possible explanations for why this happens. One is that the galaxy has fallen into a cluster, an environment where massive amounts of hot gas can strip away a galaxy's own gas supply. This process, called ram pressure stripping, happens when a galaxy moves through the dense plasma that fills galaxy clusters. The gas in the galaxy gets ripped away, like wind pushing against a cloud, leaving the galaxy unable to form new stars. Over time, the young blue stars burn out, and all that's left are the older, redder ones. But while this explains why a galaxy might turn red, it doesn't fully explain why it would still keep its spiral shape. Most galaxies that get stripped like this eventually become ellipticals. So why do some remain spirals while still losing their star-forming ability? Another possibility is that these red spirals are victims of strangulation. This means that instead of having their gas violently stripped away, they simply stop receiving new gas from their surroundings. Galaxies need a steady supply of fresh hydrogen to keep forming stars, and if that flow gets cut off, they slowly run out of fuel. Over a few billion years, their star formation grinds to a halt, and they turn red. Unlike ram pressure stripping, strangulation is a much slower process, which might explain why these galaxies still look like spirals. They haven't been disrupted violently, they've just stopped making new stars. The big question is, what's cutting off their gas supply? One idea is that they have supermassive black holes in their centers that are blasting out energy, heating up the surrounding gas and making it impossible for the galaxy to cool down and form new stars. This process, called AGN feedback, has been observed in many massive galaxies. The black hole at the galaxy's center becomes active, spewing out jets of radiation and preventing the gas from cooling. Without cool gas, stars can't form, and the galaxy slowly turns red. This would explain why red spirals still look intact. They haven't been disrupted by external forces, but rather, they've been shut down from the inside. But not all red spirals fit this pattern. Some seem to exist in isolation, far away from the dense galaxy clusters where these effects are most common. If those galaxies aren't being stripped of their gas, and they don't have an active black hole shutting down star formation, then what's happening to them? Some astronomers think that these galaxies might be undergoing a very slow and quiet form of evolution. Instead of being shut down suddenly, they could simply be using up all of their gas without getting any new supply. This could happen if a galaxy forms in a region of space where there isn't much hydrogen left to gather. Over time, it would burn through its available fuel, and when that happens, it stops forming stars. It doesn't lose its spiral shape because nothing dramatic happens to it, it just slowly fades into red. There's also the possibility that red spirals are actually a transitional phase in galaxy evolution. Maybe they aren't a separate type of galaxy at all, but rather, a brief stage that many galaxies pass through on their way from being a normal spiral to becoming an elliptical. If that's the case, then we may be catching them in the act, seeing them in a rare and temporary state before they change into something else entirely. Despite all these theories, red spirals remain a mystery. They challenge our understanding of how galaxies form, evolve, and die. If spiral galaxies can turn red without losing their structure, then it means there's a missing piece in our knowledge of the universe. Are these galaxies dying in a way we never predicted? Are they proof of an entirely new process we haven't discovered yet? Or are they relics of an ancient time, survivors of a past universe that operated under different rules? The more we study them, the more questions arise. With every new telescope we build, from Hubble to the James Webb Space Telescope and beyond, we get closer to solving the puzzle. But for now, the mystery of red spirals remains one of the strangest, most fascinating anomalies in the cosmos, one that refuses to fit into any of our neat scientific boxes. And maybe, just maybe, that's a sign that we still have a lot more to learn about the universe than we ever imagined. Red spiral galaxies don't just challenge what we know about galactic evolution, they force us to reconsider fundamental assumptions about how the universe works. If galaxies are supposed to follow a predictable life cycle, with spirals staying blue and ellipticals turning red, then why do these outliers exist? Are they the result of unique environmental factors, internal processes, or something we haven't even begun to understand? The more astronomers study them, the more complex the mystery becomes. One of the strangest aspects of red spirals is that they don't all seem to fit into a single explanation. Some appear in dense galaxy clusters, where the forces of gravitational interactions, gas stripping, and mergers could be at play. Others are found in relative isolation, far from the kind of chaotic environments that would normally quench star formation. This suggests that there might be multiple pathways leading to the same outcome, different processes that, in the end, create a red spiral galaxy. If that's true, then understanding red spirals isn't just about explaining one phenomenon, it's about uncovering a whole range of hidden mechanisms that shape the universe. Let's start with the role of galaxy mergers. When two galaxies collide, they don't necessarily merge into an elliptical shape right away. Sometimes, a merger can strip away or redistribute a galaxy's gas in a way that prevents new star formation while still keeping the original spiral structure intact. If a spiral galaxy collides with a smaller companion, the gravitational forces can disrupt its gas supply, either pushing it outward or funneling it toward the center, where it might fuel a black hole instead of forming stars. The result? A galaxy that looks like a spiral but behaves like an elliptical, no new stars, just old, red ones. But mergers don't explain everything. Many red spirals show no signs of recent collisions. That's where internal processes come into play. One possibility is that these galaxies have unusually high concentrations of dark matter, the invisible substance that makes up most of the universe's mass. Dark matter interacts with normal matter through gravity, and if a red spiral has an especially dense dark matter halo, it could subtly influence the movement of gas within the galaxy. This could slow down star formation in ways we don't fully understand yet, causing the galaxy to turn red over time without any dramatic external events. Then there's the role of magnetic fields, an often overlooked factor in galaxy evolution. Magnetic fields shape how gas moves through a galaxy, influencing everything from star formation to the way spiral arms are structured. If red spirals have unusually strong or chaotic magnetic fields, they might be affecting their own ability to form stars. This is an area of active research, and as telescopes get better at detecting cosmic magnetism, we may find that red spirals are actually telling us something profound about the hidden forces shaping the universe. Another clue lies in the distribution of red spirals across the cosmos. Studies have shown that they tend to be more common at certain distances from Earth, suggesting that they might have been more prevalent in the past and are slowly disappearing over time. If that's the case, it raises even bigger questions. Are red spirals a relic of an earlier phase in the universe's history? Did galaxies once evolve differently than they do today? If so, what changed? Answering these questions could tell us not just about individual galaxies, but about the evolution of the entire cosmos. And then there's the biggest mystery of all. Are red spirals a natural consequence of the known laws of physics, or do they hint at something deeper? Some scientists have speculated that they could be linked to dark energy, the mysterious force driving the accelerated expansion of the universe. If dark energy affects galaxies differently at different points in time, it could be subtly influencing their evolution in ways we don't yet understand. This might explain why red spirals appear more frequently at certain distances, pointing to a connection between their existence and the fundamental nature of space itself. Red spiral galaxies remain one of the strangest anomalies in the cosmos. Every time we think we're close to an answer, new data raises even more questions. They are a challenge to our understanding, a reminder that the universe is far more complex than we ever imagined. And maybe, just maybe, the key to unlocking their mystery will lead to discoveries far beyond galaxies, changing the way we see space, time, and the very nature of reality itself. The mystery of red spiral galaxies isn't just about a few strange objects scattered across the universe. It's about what they reveal about the hidden rules that govern cosmic evolution. These galaxies defy everything we thought we knew, and the more astronomers study them, the more they realize that our models of galaxy formation might be missing something crucial. One of the most puzzling aspects of red spirals is that they often show signs of past star formation, but have somehow stopped producing new stars. This is unusual because spiral galaxies typically have plenty of gas and dust, the raw materials needed to create stars. In normal spirals, this gas collapses under gravity, forming new stars that shine blue due to their high temperatures. But in red spirals, something has shut this process down. One possibility is that these galaxies have gone through a process known as quenching. Quenching happens when a galaxy loses or depletes its star-forming gas, leaving behind only older, redder stars. But how does this happen? There are a few theories. One is that red spirals might have massive black holes at their centers that are actively sucking in matter. When supermassive black holes feed, they release huge amounts of energy in the form of jets and winds. These powerful outflows can push gas away from the galaxy, preventing it from forming new stars. But not all red spirals show signs of having active black holes, which means other forces might be at play. Some scientists think that red spirals could be running out of gas simply because they're in the wrong environment. Galaxies don't exist in isolation. They are part of large cosmic structures called galaxy clusters. In these clusters, galaxies interact with each other, sometimes stealing gas or stripping it away through gravitational forces. If a spiral galaxy gets caught in one of these interactions, it might lose its star-forming gas while still maintaining its shape, eventually turning red. There's also the possibility that red spirals are an intermediate phase in galaxy evolution, meaning that they are slowly transitioning into elliptical galaxies. If this is true, then studying them could provide a rare glimpse into a stage of galactic transformation that we don't fully understand. Maybe all spiral galaxies eventually turn red before morphing into elliptical galaxies, and we just haven't observed enough of them in this stage to realize it yet. But there's another strange aspect of red spirals that raises even more questions. Some of them don't just lack new star formation, they also seem to have unusual motion patterns. When scientists measure the way stars move within these galaxies, they find unexpected velocity curves that don't match the standard models of spiral galaxies. This suggests that something strange is happening with their internal dynamics. Could it be that these galaxies have an unusual distribution of dark matter? Or is there some unknown force influencing their rotation? Dark matter plays a huge role in shaping galaxies, even though we can't see it directly. It makes up most of the mass in the universe and is responsible for holding galaxies together through gravity. If red spirals have an unusually high concentration of dark matter, it might be affecting the way their stars move and how their gas behaves. This could be one reason why they have stopped forming stars. Another strange observation is that red spirals often have fainter and more diffuse arms compared to normal spirals. This suggests that whatever process shut down their star formation also affected their structure in subtle ways. Normally, spiral arms are bright and full of young stars, but in red spirals, they appear faded and less defined. This raises the question, did red spirals form differently from the beginning, or did something change them over time? Some astronomers have proposed that red spirals might be much older than we think. If these galaxies formed billions of years ago under different cosmic conditions, they might have evolved in ways that don't match our expectations. Maybe the early universe had different rules for galaxy formation, and red spirals are relics of a time when those rules were in play. But if that's the case, why do we still see them today? If they formed under ancient conditions, shouldn't they have disappeared by now? One explanation could be that red spirals are incredibly stable structures, capable of maintaining their form for billions of years without changing much. This would be unusual, since most galaxies tend to evolve and interact with their surroundings over time. If red spirals have somehow avoided these interactions, it could mean that they exist in special cosmic environments where external forces don't affect them as much. There's also the question of how common red spirals really are. For a long time, they were considered rare, but new surveys have suggested that they might be more common than previously thought. The reason we didn't notice them before could be because older telescopes weren't sensitive enough to detect them in large numbers. But with modern observatories, like the James Webb Space Telescope, we're starting to get a clearer picture of just how widespread these galaxies might be. If red spirals turn out to be a major population of galaxies, then our entire understanding of galaxy evolution might need to be revised. Instead of being a strange exception, they could represent an important but overlooked phase of cosmic history. This could change how we think about the life cycle of galaxies and even how the structure of the universe itself has evolved over time. And then there's the ultimate question: do red spirals hold the key to understanding something even bigger? If these galaxies don't fit into our current models, does that mean there are fundamental forces at work in the universe that we don't yet understand? Could they be evidence of exotic physics, unknown cosmic interactions, or even a hint at the nature of dark energy? The deeper we dig into the mystery of red spirals, the more we realize how little we truly know about the universe. These galaxies stand as a challenge to our understanding, a reminder that even in an era of advanced telescopes and cutting-edge simulations, the cosmos still holds secrets we have yet to uncover. And maybe, just maybe, the key to solving this mystery will lead us to discoveries that change everything we thought we knew about space, time, and the fabric of reality itself. The mystery of red spiral galaxies isn't just a curiosity, it's a challenge to the very framework of how we understand the universe. Every galaxy we see today is part of a long, complex evolutionary process that spans billions of years. Spiral galaxies, in particular, are known for their dynamic, star-forming nature. So why do some of them defy expectations and turn red? The more we study these galaxies, the more it becomes clear that we're missing key pieces of the puzzle. One of the most perplexing aspects of red spirals is that they don't seem to be in the process of changing into elliptical galaxies, at least not in the way we would expect. If a spiral galaxy were simply fading into an elliptical, we would expect to see significant distortions in its shape, arms breaking apart, stars scattering, and the overall structure becoming more amorphous. But many red spirals look almost pristine. Their spiral arms are still clearly defined, their rotation patterns remain orderly, and yet, their ability to form new stars has been completely shut down. This raises a crucial question. Are red spirals a dead end in galactic evolution, or are they in a state we just don't fully understand yet? If they are truly in a transitional phase, then we should be able to find young red spirals that are just beginning this process, and older ones that are closer to becoming ellipticals. But so far, astronomers haven't been able to identify a clear timeline for this transformation. Instead, red spirals appear to exist in a strange limbo, no longer forming new stars, but also not showing clear signs of further evolution. One possible explanation involves the cosmic web, the vast, interconnected structure of filaments and voids that make up the large-scale structure of the universe. Galaxies don't just float randomly in space. They are connected through these massive cosmic filaments, which channel gas, matter, and even energy. Some astronomers believe that red spirals might have been cut off from these filaments, essentially starving them of the fresh gas they need to keep forming stars. If this is true, then the reason red spirals exist might not be due to internal processes at all, but rather, their placement within the larger cosmic structure. Galaxies in certain regions of the universe might be more likely to become red spirals simply because they are located in areas where gas replenishment is limited. If we can map the locations of red spirals in relation to the cosmic web, we might be able to determine whether their existence is tied to their position in the universe rather than their individual history. Another factor to consider is the role of dark energy. We know that dark energy is causing the expansion of the universe to accelerate, but what if it's also influencing galaxies on a smaller scale? Some researchers have suggested that dark energy might not be a uniform force but could have variations in strength across different regions of space. If red spirals exist in areas where dark energy effects are stronger, it could be influencing the way their gas behaves, subtly suppressing star formation over time. This idea is highly speculative, but it highlights an important point. Red spirals might be telling us something fundamental about forces in the universe that we don't yet understand. If we can figure out what makes these galaxies different, we might unlock new insights into the nature of dark energy, dark matter, and even the overall evolution of cosmic structures. One of the biggest challenges in studying red spirals is that they are relatively rare compared to normal spiral, or elliptical galaxies. This makes it difficult to gather enough data to build a comprehensive theory about them. But as new telescopes come online, particularly ones designed to study the universe in greater detail, we are starting to detect more of these galaxies than ever before. The Vera C. Rubin Observatory, for example, is expected to provide a massive influx of new galactic data in the coming years. This telescope will conduct a 10-year survey of the sky, capturing detailed images of millions of galaxies. With this data, astronomers will be able to analyze red spirals in greater numbers than ever before, looking for patterns in their locations, structures, and compositions. If we find that red spirals are concentrated in certain environments, that could be a strong clue that external factors, like interactions with the cosmic web or dark energy, are playing a major role. If, on the other hand, we find that red spirals appear randomly across all kinds of environments, then we might need to rethink our ideas about how galaxies evolve internally. Another exciting tool in this search is the James Webb Space Telescope. Unlike previous telescopes, Webb is capable of peering deep into the infrared spectrum, allowing it to study galaxies in greater detail than ever before. This could help us analyze the chemical composition of red spirals, giving us insights into whether they still contain hidden gas reservoirs or if their star-forming materials have been completely depleted. There's also a growing interest in using artificial intelligence to study red spirals. With so much astronomical data being collected, AI algorithms are increasingly being used to identify patterns that human researchers might miss. Machine learning models could analyze thousands of galaxies at once, searching for common traits among red spirals and potentially revealing new clues about their origins. But even with all these advancements, red spirals remain an enigma. They don't fit neatly into our current models, and every new discovery seems to raise more questions than answers. Are they a relic of a past cosmic era, or do they represent an entirely new category of galaxy evolution? Could they be evidence of unknown physical processes at play in the universe? One thing is certain: solving the mystery of red spirals won't just help us understand these galaxies. It will help us refine our understanding of how the entire universe works. Every anomaly in astronomy is an opportunity. The fact that these galaxies exist means that something unexpected is happening, something that doesn't fit into our standard models. And every time scientists encounter something that doesn't fit, it's usually a sign that a major discovery is waiting just beyond the horizon. In many ways, red spirals are like cosmic fossils, preserving information about the forces that shaped them over billions of years. By studying them, we might be able to uncover hidden processes that have been shaping galaxies for as long as the universe has existed. And who knows? The answers we find might not just explain red spirals, they might change our entire view of the cosmos itself. As we push deeper into the mystery of red spirals, one thing becomes increasingly clear: these galaxies defy simple explanations. Every attempt to categorize them within known galactic evolution models runs into contradictions. They look like spirals, yet behave like ellipticals. They have the structure of young, active galaxies but the dull, aged glow of galaxies that should be long past their star-forming years. This paradox forces us to rethink not just how galaxies evolve, but what hidden forces might be acting on them. One particularly strange aspect of red spirals is that some of them seem to contain just enough gas to form stars, but don't. This is unusual because in most galaxies, gas and star formation go hand in hand. If gas is present and cool enough, it collapses under gravity and forms new stars. So why is this process shutting down in red spirals, even when the raw materials are still there? One possible explanation is that red spirals have undergone a process called strangulation. This means that while they still contain some gas, their ability to bring in fresh gas has been cut off. Over time, this leads to a slow, silent death of star formation. But the big question is, what's causing this strangulation? Some scientists suspect that it's due to the environments these galaxies live in. If a red spiral is part of a galaxy cluster, it might be feeling the effects of a process called ram pressure stripping. Imagine a galaxy moving through a dense cloud of hot plasma that fills a galaxy cluster. As the galaxy moves through this environment, the pressure from the surrounding gas can push out its own supply of star-forming gas, like wind blowing the leaves off a tree. Once the gas is gone, the galaxy loses its ability to create new stars, and over time, it fades into a reddish color. But not all red spirals are found in clusters, which means this can't be the only explanation. Another possibility involves feedback from supermassive black holes. Almost every galaxy has a supermassive black hole at its center, and when these black holes become active, they can release massive amounts of energy. This energy can heat up or blow away the gas in a galaxy, making it impossible for new stars to form. Some red spirals show signs that their central black holes might have played a role in shutting down their star formation. But even this explanation has problems. If black hole activity were the main cause of red spirals, we would expect to see more clear signs of violent energy releases in these galaxies. Instead, many of them appear surprisingly undisturbed, as if their transformation into red spirals happened gradually rather than suddenly. Some astronomers have suggested that red spirals might actually be a remnant of a long-lost population of galaxies. In the early universe, galaxies were forming stars at an incredible rate. If some of those ancient galaxies evolved differently than the ones we see today, it's possible that red spirals are the last survivors of an evolutionary path that never became dominant. In other words, they might not be a transition phase at all. They might be an entirely separate type of galaxy that has existed for billions of years, unnoticed because of their rarity. If this is true, then red spirals could hold clues about what galaxies were like in the early universe. By studying them, we might be able to get a glimpse of a time when galaxy evolution followed different rules, shaped by conditions that no longer exist today. This would make red spirals not just an anomaly, but a time capsule, an opportunity to peer back into a forgotten chapter of cosmic history. One of the biggest breakthroughs in understanding red spirals might come from studying their dark matter halos. Every galaxy is surrounded by a vast, invisible halo of dark matter, which provides the gravitational framework that holds it together. If red spirals have unusually dense or differently shaped dark matter halos, this could explain why their evolution has been so unusual. Some theories suggest that dark matter interactions might play a direct role in shutting down star formation. If dark matter in red spirals is clumpier or more concentrated than in normal spirals, it could be disrupting the flow of gas in ways we don't yet understand. Alternatively, if red spirals have been influenced by unseen interactions with other dark matter structures in the universe, this could have altered their evolution in ways that don't match our current models. This idea is difficult to test because dark matter is, by definition, invisible. But new techniques in gravitational lensing, the bending of light by massive objects, could provide indirect evidence of unusual dark matter distributions around red spirals. If we find that red spirals have different dark matter properties compared to other galaxies, this could be a game-changer in our understanding of both galaxy evolution and the nature of dark matter itself. One of the most fascinating possibilities is that red spirals are evidence of an unknown cosmic force, something beyond dark matter and dark energy that is influencing galaxies in ways we haven't yet identified. Could there be a fifth fundamental force at play, subtly shaping the evolution of galaxies? Some physicists have proposed that exotic particles or undiscovered forces might be interacting with galaxies on large scales, altering their behavior in unexpected ways. While this idea is highly speculative, red spirals provide an intriguing testing ground for such theories. If they truly don't fit into any known evolutionary paths, then we have to start asking bigger questions about the nature of the universe itself. What if our entire understanding of how galaxies evolve is missing a key ingredient? One way to investigate this further is to compare red spirals with galaxies in different parts of the universe. If we find that red spirals are more common in certain regions of space, this could suggest that local cosmic conditions play a major role in their formation. If, on the other hand, they appear randomly distributed, this might mean that their unique properties come from internal processes rather than external forces. As more advanced telescopes come online, we are entering an era where we can study galaxies in unprecedented detail. The upcoming Extremely Large Telescope, ELT, will be able to resolve individual stars and distant galaxies, allowing astronomers to analyze the internal structures of red spirals in ways that were previously impossible. By doing so, we may finally be able to determine whether these galaxies are dying spirals, relics of an ancient past, or something else entirely. Red spirals remain one of the most puzzling phenomena in astrophysics. They challenge our assumptions about how galaxies live and die, forcing us to consider new ideas about the forces that shape the universe. Whether they are a missing link in galaxy evolution, a relic of a forgotten cosmic era, or evidence of unknown physics, one thing is certain: they demand our attention. And perhaps, as we continue to study them, we'll uncover answers not just about red spirals, but about the very fabric of reality itself. Because every mystery in space, no matter how small, has the potential to rewrite everything we think we know about the cosmos. The deeper we investigate the mystery of red spirals, the more we realize how much they challenge our understanding of the universe. At their core, these galaxies appear to defy classification, forcing astronomers to question fundamental assumptions about galactic evolution. Could it be that our current models of how galaxies form, grow, and die are missing a crucial piece of the puzzle? If so, then red spirals might be the key to unlocking a new perspective on the forces that shape the cosmos. One major issue is that red spirals blur the line between two well-established categories of galaxies. Traditional spiral galaxies are known for their bright, blue appearance, packed with young stars and actively forming new ones. On the other hand, elliptical galaxies, which are typically red, have exhausted most of their star-forming gas and settled into a quiet, passive state. Red spirals, however, appear to be a bizarre mix of both. They maintain the spiral structure of young, active galaxies while displaying the reddish hue of old, inactive ones. This contradiction raises an important question. Are red spirals galaxies in transition, caught in the middle of a dramatic transformation, or are they an entirely separate class of galaxies that have followed an alternative evolutionary path? To get closer to an answer, astronomers have analyzed the environments in which red spirals are found. A significant number of them appear in dense galaxy clusters, where interactions between galaxies are common. When galaxies move through a cluster, they are subjected to strong gravitational forces that can distort their shapes, strip away their gas, and disrupt their internal processes. This environment provides a possible explanation for how red spirals form. Perhaps they were once ordinary blue spirals, but after encountering a denser region of space, their gas was gradually stripped away, halting star formation and causing them to take on a reddish hue. But here's where things get complicated. Not all red spirals exist in clusters. Some are found in relatively isolated regions of space, far from the gravitational disturbances of large galaxy groups. This suggests that there may be multiple pathways for a galaxy to become a red spiral, and not all of them involve external interactions. Some internal process within the galaxies themselves may be shutting down star formation. One possibility is that red spirals are the result of unusually strong internal feedback from their central black holes. Every large galaxy is thought to contain a supermassive black hole at its core, and when these black holes become active, they can release powerful jets of energy. These jets can heat up the surrounding gas or even expel it from the galaxy altogether, preventing new stars from forming. If red spirals have particularly active black holes, this could explain why they have stopped forming stars while still retaining their spiral shape. However, observations show that not all red spirals have obvious signs of black hole activity. In fact, some appear surprisingly undisturbed, as if their transformation was a slow and subtle process rather than a violent event. This raises another question: could there be a hidden force at work, one that we have yet to fully understand? Some astronomers have proposed that red spirals might be evidence of a previously unknown mechanism of galaxy evolution. One intriguing idea is that dark matter, the invisible substance that makes up most of the universe's mass, could be playing a more active role in shaping galaxies than we realize. If red spirals have unusually dense dark matter halos, these halos might be interfering with the way gas moves within the galaxy, preventing it from collapsing into new stars. Alternatively, dark matter interactions with ordinary matter might be causing a slow loss of star-forming material over billions of years. Testing these ideas is difficult because dark matter is invisible and can only be detected through its gravitational effects. But by studying the motions of stars and red spirals, astronomers can indirectly measure the distribution of dark matter within them. If these galaxies do indeed have unique dark matter properties, it could revolutionize our understanding of how galaxies evolve and how dark matter itself interacts with normal matter. Another hypothesis suggests that red spirals could be relics from an earlier time in the universe's history. In the distant past, galaxies were forming stars at an incredible rate, but not all of them followed the same evolutionary path. Some may have developed in a way that made them unusually prone to shutting down star formation early on, long before most galaxies of their type did. If this is the case, then red spirals might not be transitioning from one state to another at all. They might simply be an ancient class of galaxies that has persisted throughout cosmic history. This idea is particularly exciting because it suggests that red spirals could offer a window into the conditions of the early universe. If they are truly remnants of a lost galactic population, then studying them could reveal what the universe was like billions of years ago, providing clues about how galaxies formed in the first place. There's also the possibility that red spirals are not a single phenomenon but rather a collection of different types of galaxies that happen to share similar characteristics. Some may have become red spirals due to interactions with their environment, while others may have evolved that way naturally. This would mean that red spiral is not a specific stage in galaxy evolution but rather a broad category that encompasses multiple evolutionary pathways. As new telescopes come online, such as the James Webb Space Telescope and the upcoming Extremely Large Telescope, astronomers will have the ability to study red spirals in greater detail than ever before. These telescopes will be able to peer deeper into space and capture higher-resolution images, allowing scientists to analyze the internal structures of red spirals and their surrounding environments. One approach to solving the mystery is to look for more red spirals in the early universe. If red spirals were common billions of years ago but rare today, this would support the idea that they are remnants of an ancient galactic population. On the other hand, if they appear to be just as rare in the early universe as they are now, this would suggest that they are a product of specific conditions rather than a natural stage of galaxy evolution. Another approach involves mapping the distribution of red spirals across the cosmos. If red spirals are clustered in specific regions of the universe, this might indicate that local cosmic conditions play a major role in their formation. But if they appear randomly scattered, this could suggest that their properties are driven by internal factors rather than external influences. Ultimately, the mystery of red spirals is a reminder of how much we still don't know about the universe. Every time we think we have a clear picture of how galaxies evolve, a new discovery challenges our assumptions and forces us to rethink our models. Red spirals might be a missing link in our understanding of galactic evolution, a relic of a forgotten cosmic era, or even evidence of unknown physics at play. Whatever the answer turns out to be, one thing is certain: red spirals are more than just an oddity. They represent a fundamental challenge to our understanding of the cosmos, and solving their mystery could lead to breakthroughs that reshape how we view the universe itself. And perhaps, just perhaps, as we continue to explore these enigmatic galaxies, we'll stumble upon something even stranger, something that changes everything we thought we knew about the nature of space, time, and reality. The search for answers about red spirals leads us deeper into the fabric of the cosmos, forcing us to confront the limits of our understanding. Every piece of evidence we uncover adds another layer of complexity to the puzzle, suggesting that these galaxies may hold secrets far beyond what we initially imagined. If red spirals are the missing link in galactic evolution, then unlocking their mysteries could reshape our entire understanding of how galaxies grow, change, and eventually fade into the cosmic background. One of the most perplexing aspects of red spirals is their stubborn refusal to conform to existing models of galaxy classification. For decades, astronomers have relied on a well-established system that separates galaxies into distinct categories based on their structure and color. Spiral galaxies, with their bright blue arms, are expected to be active sites of star formation, while elliptical galaxies, with their featureless, reddish appearance, are assumed to be mostly inactive. But red spirals break these rules. They retain their spiral arms, suggesting that they should be forming stars, yet their reddish color indicates that they are not. This contradiction raises a disturbing possibility. What if our entire understanding of how galaxies evolve is missing a crucial piece? One theory suggests that red spirals are the victims of an internal struggle, an unseen battle between forces that promote star formation and those that suppress it. At the heart of this struggle is the balance between gas availability and the forces that regulate it. In most galaxies, star formation is fueled by vast reservoirs of cold hydrogen gas. When this gas cools and collapses under gravity, it forms new stars, lighting up the galaxy in brilliant shades of blue. But in red spirals, this process seems to have stalled. The question is, why? One explanation could be that red spirals are undergoing a slow strangulation process, where the supply of fresh gas needed for star formation has been gradually cut off. This could happen in multiple ways. In galaxy clusters, for example, the high-energy environment can strip gas away from galaxies as they move through the dense intracluster medium. This process, known as ram pressure stripping, could rob red spirals of their star-forming material while leaving their structure intact. But this explanation doesn't account for isolated red spirals, which exist far from the chaotic environments of galaxy clusters. This suggests that internal processes might be just as important, if not more so, than external factors. One of the leading candidates is feedback from supermassive black holes. When black holes consume matter, they release enormous amounts of energy, often in the form of powerful jets or intense radiation. If a red spiral's central black hole is particularly active, it could be heating up or expelling the surrounding gas, preventing it from cooling and forming new stars. Some red spirals show evidence of this kind of activity, but others do not, making it unclear whether black holes alone are responsible. Another possibility is that red spirals are the result of a rare evolutionary pathway, one that is not yet fully understood. Some astronomers propose that these galaxies were once normal, star-forming spirals but underwent a slow and quiet shutdown of star formation without any dramatic external event. This could be due to subtle changes in the way gas moves within the galaxy, or even the influence of dark matter, which may be affecting the overall stability of the gas supply. Dark matter, the invisible substance that makes up most of the universe's mass, has long been suspected of playing a key role in galaxy formation. But what if it also has an impact on how galaxies die? Some theories suggest that red spirals might be surrounded by unusually dense halos of dark matter, which could be affecting their ability to retain or recycle gas. If dark matter halos are interacting with normal matter in unexpected ways, it could be disrupting the flow of star-forming material, leading to a gradual shutdown in activity. This idea is difficult to test directly, but astronomers have begun looking for clues in the rotation patterns of red spirals. By measuring the speeds of stars at different distances from the center of these galaxies, they can infer the distribution of dark matter. If red spirals have significantly different rotation patterns compared to normal spirals, it could point to a hidden influence that we have yet to fully understand. Adding another layer of mystery is the question of whether red spirals are a temporary phase in galactic evolution or a permanent state. If they are transitioning toward becoming elliptical galaxies, then we should see evidence of their spiral structures slowly dissolving over time. But observations show that many red spirals maintain their structure for billions of years, suggesting that they are not necessarily on a one-way path to becoming ellipticals. Instead, they might represent a stable, but rare, alternative to the traditional spiral and elliptical classifications. If red spirals truly are their own distinct class of galaxies, then they challenge one of the fundamental assumptions of astrophysics, that all galaxies follow a predictable evolutionary path. The discovery of these galaxies suggests that there may be multiple ways for a galaxy to evolve, some of which we are only beginning to uncover. This could mean that our current models need to be revised, or even completely rethought, to account for these alternative pathways. One of the biggest challenges in solving the red spiral mystery is their rarity. They make up only a small fraction of all known galaxies, which makes studying them difficult. Large-scale galaxy surveys, such as the Sloan Digital Sky Survey, have helped identify more examples, but we still lack a complete picture of how widespread they are across the universe. Are they a phenomenon unique to certain cosmic epochs, or have they existed throughout the history of the universe? To answer this, astronomers are looking deep into cosmic time, using powerful telescopes to search for red spirals in the early universe. If they find that red spirals were more common in the past, it could indicate that these galaxies represent an earlier, now largely extinct phase of galactic evolution. But if they remain rare even in the distant universe, it could mean that they form under highly specific conditions that are not well understood. The upcoming generation of telescopes, including the James Webb Space Telescope and future ground-based observatories, will play a crucial role in unraveling the mystery. These instruments will allow astronomers to study red spirals with unprecedented detail, analyzing their chemical compositions, internal dynamics, and surrounding environments. This could provide the final pieces of the puzzle, revealing whether these galaxies are a transitional phase, a relic of the past, or something entirely new. What makes the mystery of red spirals so fascinating is that it goes beyond just one type of galaxy. It touches on some of the biggest questions in astrophysics: how galaxies evolve, what role dark matter plays in shaping the universe, and whether our current models of galaxy formation are incomplete. The fact that these galaxies exist at all suggests that the universe still holds surprises, waiting to be uncovered. And perhaps the biggest question of all remains unanswered: if red spirals are just one example of a galaxy that defies classification, what else might be out there? Are there other hidden populations of galaxies that don't fit into our current categories? Could there be entire classes of galaxies that we have yet to discover, lurking in the depths of the cosmos? The more we explore, the more we realize that the universe is far more complex and mysterious than we ever imagined. Red spirals are just one piece of the puzzle, but they may be the key to unlocking secrets that go far beyond their strange and contradictory nature. The deeper we dig into the mystery of red spirals, the more questions seem to arise. If these galaxies don't fit neatly into our current understanding, could they be pointing us toward an entirely new framework for galactic evolution? Could it be that the way we classify galaxies, spiral, elliptical, irregular, is too simplistic to capture the full diversity of the universe? Red spirals may not just be an anomaly. They could be evidence that our entire system of categorization needs to be expanded. To get closer to an answer, astronomers are studying the environments in which red spirals are found. One of the more surprising discoveries is that many red spirals exist in relatively isolated regions of space. This is strange because most red galaxies, especially ellipticals, are typically found in dense galaxy clusters, where interactions with other galaxies can strip away gas and shut down star formation. But red spirals don't seem to follow this trend. Instead, some are found in the outskirts of clusters, while others exist in complete isolation. This raises another possibility. Could red spirals be a result of past interactions rather than ongoing ones? Some simulations suggest that these galaxies may have undergone a process known as harassment. This happens when a galaxy moves through a dense region and experiences multiple gravitational interactions with other galaxies. These encounters don't necessarily lead to full mergers but can be enough to disrupt the gas flow within the galaxy, leading to a slowdown, or even a complete stop, in star formation. Another theory suggests that red spirals could be the remnants of past galactic mergers. When two galaxies collide, the process often triggers a burst of star formation, but it can also result in the loss of gas, either through intense radiation pressure or through the expulsion of gas into intergalactic space. If a spiral galaxy went through such an event, it could have lost its ability to form new stars while still maintaining its spiral structure. However, this explanation is not entirely satisfactory, because most galaxy mergers tend to distort spiral structures, turning them into something more irregular or elliptical. The fact that red spirals retain their delicate arms suggests that if a past merger did occur, it must have been highly unusual. This leads to an even stranger idea. What if red spirals are not just galaxies in transition but rather a stable, long-term state that we haven't recognized before? Most of our models assume that galaxies move through specific evolutionary stages, from blue spirals to red ellipticals. But what if some galaxies are simply different from the beginning? Could red spirals represent a fundamentally distinct type of galaxy, one that has existed since the early universe but has remained largely unnoticed because of their rarity? To investigate this, astronomers have started looking at the ages of the stars within red spirals. If these galaxies are truly distinct from normal spirals, we might expect to find that their stars are systematically older. Initial studies suggest that many red spirals do indeed contain older stellar populations, which supports the idea that they have been in their current state for billions of years. But the picture is not so clear-cut. Some red spirals show signs of younger stars, indicating that star formation has not completely shut down. This complicates the question further. If red spirals are not entirely dead, then what is keeping them on the edge of dormancy? Some researchers have proposed that red spirals may still be forming stars but at an incredibly slow rate. Instead of the rapid bursts of star formation seen in blue spirals, red spirals may be experiencing a form of simmering star formation, where small pockets of gas are slowly converted into new stars over time. If this is true, then red spirals could be the astrophysical equivalent of a slow-burning fire, never fully extinguished, but never burning brightly either. Another clue lies in the chemical composition of red spirals. By analyzing the spectral lines in their light, astronomers can determine what elements are present in these galaxies. The results are intriguing. Red spirals appear to have higher amounts of heavy elements compared to normal spirals. This suggests that these galaxies have gone through multiple generations of star formation in the past, enriching their gas with elements like oxygen, carbon, and iron. But if that's the case, why did they stop forming stars? Did they simply run out of usable gas, or is there another factor preventing them from reigniting? Some researchers speculate that magnetic fields could be playing a role. Magnetic fields are often overlooked in galaxy evolution studies, but they can have a profound impact on how gas moves within a galaxy. If a red spiral has an unusually strong magnetic field, it could be affecting the ability of gas to collapse and form new stars. This is still a highly speculative idea, but if true, It would open up an entirely new dimension to our understanding of galaxy evolution, one where magnetic forces act as an invisible hand, shaping the fates of entire galaxies. And then there's the strangest possibility of all. What if red spirals are influenced by unknown physics? Could we be looking at evidence of some hidden cosmic process that we have yet to discover? The idea might seem far-fetched, but history has shown that some of the biggest breakthroughs in astronomy have come from anomalies, strange observations that didn't fit the existing models. The discovery of dark matter, for example, was driven by the realization that galaxies were rotating in ways that defied gravitational calculations. The red spirals could be another such anomaly, hinting at physics beyond what we currently understand. Perhaps the most fascinating aspect of the red spiral mystery is that it forces us to question our own assumptions. We like to think of the universe as something that follows clear, predictable rules, but time and again, reality has shown itself to be far more complex. The existence of red spirals challenges our confidence in the models we use to explain the cosmos, reminding us that there is still so much we don't know. And that brings us back to the biggest question of all. Why do red spirals exist? Are they a rare glitch in the cosmic order, or are they an overlooked key to understanding something much bigger? Until we find a definitive answer, red spirals will continue to haunt the edges of our knowledge, reminding us that even in the vast, seemingly well-mapped universe, there are still secrets waiting to be uncovered. But the search for answers is far from over. In the coming years, new telescopes, new simulations, and new theories will bring us closer to the truth. Perhaps one day, we'll look back at red spirals not as an unsolved mystery, but as the first clue to a groundbreaking discovery about the nature of galaxies, the role of dark matter, or even the fundamental laws of physics themselves. Until then, the mystery remains, and the universe continues to challenge us with questions we never even thought to ask. The deeper astronomers dig into the enigma of red spirals, the more it becomes clear that these galaxies are not just a minor anomaly but a challenge to the very foundations of how we classify and understand the universe. At first glance, it might seem like these galaxies are just an odd exception, a spiral galaxy that somehow ran out of gas too early or an elliptical galaxy that stubbornly clung to its spiral arms. But as more and more red spirals are discovered, it becomes clear that this is not an isolated phenomenon. Something larger is at play. One of the most intriguing aspects of red spirals is that they don't seem to fit into any natural evolutionary pathway. Traditional galaxy evolution follows a rough trajectory. Young galaxies form stars rapidly, giving them a bright blue color, and over billions of years, as their gas supply runs out, they turn red and become ellipticals. This process is driven by interactions with other galaxies, internal processes, and sometimes dramatic events like mergers or black hole activity. But red spirals seem to have skipped a step. They haven't turned into ellipticals, but they also aren't forming stars at the rate expected for their shape. To understand this better, astronomers have turned to detailed simulations, recreating different scenarios in which a galaxy could end up in this state. One of the leading explanations is that red spirals might have once been normal blue spirals but were affected by a slow strangulation process, something that gradually cut off their ability to form new stars while leaving their structure intact. But what could cause such a thing? One possibility is that these galaxies fell into a galaxy cluster at some point in the past. Galaxy clusters are crowded environments where interactions between galaxies happen frequently. When a spiral galaxy enters such a cluster, it can be stripped of its gas through a process called ram pressure stripping. Essentially, as the galaxy moves through the hot plasma that fills galaxy clusters, its own gas is slowly pulled away, like air being pushed out of a moving car. Over time, this means the galaxy loses the ability to form new stars, even though its spiral structure remains. But this explanation doesn't fit all red spirals. Many of these galaxies are found in isolation, far from the dense environments where ram pressure stripping occurs. This suggests that whatever is shutting down star formation in red spirals must be happening through internal processes rather than external ones. One leading idea is that red spirals are being starved of fresh gas because of feedback from their central black holes. Every large galaxy is thought to have a supermassive black hole at its center, and in some cases, These black holes can be extremely active, releasing powerful jets of energy that heat up and expel the surrounding gas. If a spiral galaxy's black hole enters a prolonged period of high activity, it could effectively shut down star formation by preventing cold gas from condensing into new stars. This would create a scenario where the galaxy remains structurally intact but can no longer produce new blue stars, leaving behind only the older, redder stars that dominate its light. This theory is supported by observations showing that many red spirals have unusually bright and active galactic centers, suggesting that their black holes may have played a role in their transformation. But this explanation still has its own complications. Not all red spirals have evidence of black hole activity, and some show signs of weak but ongoing star formation, which shouldn't be the case if black hole feedback were the primary cause. Another possibility is that red spirals formed differently from the very beginning. Instead of being normal spirals that lost their ability to form stars, they could represent a distinct type of galaxy that has existed in this state for billions of years. Some models suggest that certain galaxies may have formed in environments where gas was already scarce, leading them to develop a spiral structure but never go through the same intense star formation burst seen in traditional blue spirals. If this is the case, then red spirals might not be dead versions of normal spirals, but rather an entirely separate class of galaxies that we simply haven't recognized before. To test this idea, astronomers have been looking at the elemental composition of stars in red spirals. If these galaxies were once normal blue spirals that lost their gas, their older stars should have chemical signatures similar to other spirals, just without the presence of younger, more metal-poor stars. But if red spirals have always been different, we would expect their stars to show a unique chemical fingerprint. Some preliminary studies suggest that red spirals do, in fact, have unusual chemical compositions compared to typical spirals, but more data is needed before any definitive conclusions can be drawn. The implications of this mystery extend far beyond just understanding one peculiar type of galaxy. If red spirals are a missing piece of galaxy evolution, then our entire understanding of how galaxies grow and change over time might need to be revised. Could there be other types of galaxies out there that don't fit into our neat categories of spirals, ellipticals, and irregulars? Are we missing other hidden populations of galaxies that defy classification? This is where new technology will play a crucial role. With the advent of powerful telescopes like the James Webb Space Telescope and upcoming large-scale sky surveys, astronomers are gaining the ability to look deeper into the universe than ever before. These tools could reveal new details about red spirals, helping us understand their true origins. Do they contain hidden reservoirs of gas that we've missed? Are there faint signals of past interactions that we haven't detected? Could they be connected to the formation of dark matter structures in ways we don't yet understand? Perhaps the biggest lesson of the red spiral mystery is that the universe is still full of surprises. Every time we think we have a complete picture of how things work, nature finds a way to remind us that we are still just scratching the surface. The discovery of red spirals is not just about a few unusual galaxies. It's a reminder that even the most fundamental ideas in astronomy can still be challenged. The mystery of red spirals may take decades to fully unravel. Or perhaps, like many cosmic mysteries before it, the answer will come from an unexpected direction, some breakthrough in physics, some new discovery about dark matter, or some yet unknown force shaping galaxies in ways we never imagined. Until then, red spirals will remain an open question, a challenge to astronomers, and a symbol of the boundless complexity of the universe. But the story doesn't end here. There's still so much more to uncover, and the deeper we look, the stranger things seem to get. What other cosmic mysteries are waiting to be found? What secrets are hidden in the light of distant galaxies, in the movements of the stars, in the unseen forces that shape our universe? The mystery of red spirals is just one piece of a much larger puzzle, one that we are only beginning to understand. The mystery of red spirals challenges not just our understanding of galaxy evolution, but also the broader assumptions we make about how the universe functions. When astronomers first began systematically classifying galaxies, they assumed that shape and color were directly linked to a galaxy's life cycle. Spirals were blue, ellipticals were red, and there was a natural progression from one to the other. But the existence of red spirals breaks that pattern, forcing us to consider that there may be multiple, hidden evolutionary pathways that we have yet to uncover. One of the biggest questions still unanswered is whether red spirals are a temporary phase in a galaxy's evolution or a long-term, stable state. If they are simply spirals that are slowly transitioning into ellipticals, then we would expect to find a higher number of them in environments where galaxy interactions are frequent, such as galaxy clusters. This would suggest that many red spirals we see today will eventually lose their shape and become more spherical over time. However, if red spirals are instead a stable galaxy type that has existed for billions of years without significant change, then this would imply a completely different formation history, one that doesn't follow the traditional spiral to elliptical pathway at all. To get closer to the answer, astronomers have been looking at the internal dynamics of red spirals. By measuring the movement of stars within these galaxies, we can get clues about how they formed and evolved. A key question is whether their spiral arms are still rotating in the same way as younger, blue spirals. If the motion of stars in red spirals is more chaotic, with stars orbiting in random directions, this would suggest that they are in the process of becoming elliptical galaxies. But if their rotation is still highly organized, then it could mean that red spirals are fundamentally different from normal spirals in ways we don't yet understand. Interestingly, some red spirals show evidence of an unusual feature known as a pseudobulge. In many galaxies, the central bulge is thought to be a relic of past mergers, formed when galaxies collide and their central regions become denser. But pseudobulges are different. They appear to form gradually through internal processes rather than sudden, violent events. This raises the possibility that red spirals didn't necessarily undergo dramatic galaxy interactions but instead evolved in a slow, steady manner over billions of years. Another potential clue lies in the distribution of dark matter within red spirals. Dark matter is an invisible form of matter that makes up most of the universe's mass, and its gravitational pull plays a crucial role in shaping galaxies. If red spirals have unusually high concentrations of dark matter compared to normal spirals, it could mean that their evolution has been influenced by hidden forces that we don't yet fully understand. To explore this, researchers have been studying the gravitational lensing effects of red spirals, how their gravity bends the light of more distant objects. By measuring these distortions, scientists can infer how much dark matter is present in and around these galaxies. Some preliminary findings suggest that red spirals might indeed have different dark matter distributions compared to normal spirals, but the data is still inconclusive. If this pattern holds, it could mean that the formation of red spirals is tied to interactions with dark matter in ways that challenge our current models of galaxy evolution. One of the biggest open questions is whether red spirals are more common in the early universe. If they were once much more abundant and have since faded away, it would suggest that they represent a transitional phase that only lasted for a certain period in cosmic history. To investigate this, astronomers are using telescopes like the James Webb Space Telescope to look at galaxies from billions of years ago, essentially looking back in time to see if red spirals were more common in the past. If we do find evidence of ancient red spirals, it could mean that they were a more common galaxy type in the early universe but have since been replaced by other structures. But if red spirals appear to be just as rare in the distant past as they are today, then it would suggest that whatever causes them is something that happens under very specific conditions, rather than being a normal stage of galaxy evolution. One of the strangest possibilities that has been suggested is that red spirals might be connected to an unknown cosmic process, something beyond what we currently understand about galaxy formation. Could they be remnants of an earlier cosmic era, formed under different physical conditions than the galaxies we see today? Could they be linked to exotic physics, such as interactions with hidden dimensions or modifications to our understanding of gravity? While these ideas are speculative, they highlight the fact that we still don't have a complete picture of how galaxies evolve. This is what makes the mystery of red spirals so compelling. Unlike some cosmic puzzles that can be explained by minor tweaks to existing theories, red spirals challenge some of the most fundamental assumptions we make about the universe. They suggest that the way we categorize galaxies might be too simplistic and that there could be entire classes of galaxies that we haven't even recognized yet. As technology advances and our ability to observe the universe improves, we may one day have a clear answer to the mystery of red spirals. But until then, they remain a reminder that the universe is far more complex than we ever imagined. The more we learn, the more we realize how much we still don't know. What other surprises are out there, waiting to be discovered? The mystery of red spirals raises even deeper questions about the nature of galactic evolution and the forces shaping the universe. If these galaxies don't fit neatly into our current understanding, what else are we missing? Could there be other overlooked galactic structures that defy classification? And if red spirals are a stable, long-lived type of galaxy rather than a temporary transition phase, what does that mean for our models of cosmic history? One particularly intriguing aspect of red spirals is the presence of older, red stars in a structure that should theoretically still be forming new stars. In typical blue spirals, the ongoing process of star formation is fueled by the collapse of gas clouds, which then produce new, hot, blue stars. Over time, these stars age and turn red as they cool. In a red spiral, however, star formation has largely shut down, leaving behind only the older, redder population of stars. But how does this process happen without the galaxy losing its spiral structure? In normal conditions, when a galaxy stops forming new stars, its structure tends to change as well. The lack of new star formation leads to gravitational interactions that slowly disrupt the spiral arms, causing them to fade or transition into a more elliptical shape. Yet red spirals retain their distinct arms, meaning that whatever caused their star formation to stop must have done so without affecting the structural integrity of the galaxy. Some scientists speculate that red spirals might have exhausted their available star-forming gas in a way that prevented them from becoming elliptical galaxies. This could have happened due to internal processes, such as unusually efficient star formation that rapidly depleted their gas supply. If a red spiral used up its gas much faster than a typical blue spiral, it would reach a state where no new stars could form, even though its spiral arms remained intact. Another possibility is that red spirals underwent an interaction with their surroundings that stripped away their gas but left their structure untouched. This could happen if a galaxy passed through a dense intergalactic medium, where external forces could remove its gas without disturbing its stars. In galaxy clusters, a process known as ram pressure stripping can strip gas away from galaxies moving through the hot plasma of the cluster environment. If red spirals experienced a mild form of this process, they could have lost their star-forming material while still maintaining their shape. However, not all red spirals are found in galaxy clusters. Some exist in isolated regions of space, where external gas stripping would be unlikely. This suggests that multiple pathways might lead to the formation of a red spiral, rather than a single, universal cause. Another intriguing clue comes from the distribution of supermassive black holes in red spirals. Every large galaxy is thought to host a supermassive black hole at its center, and the activity of this black hole can influence the galaxy's ability to form stars. If a black hole is actively feeding on surrounding matter, it can release powerful jets and winds that heat up or expel gas, preventing new stars from forming. Some observations suggest that red spirals might have unusually active black holes compared to typical blue spirals. This raises the possibility that internal black hole activity played a role in shutting down star formation within these galaxies. If a red spiral's black hole went through a particularly intense period of feeding, it might have released enough energy to permanently disrupt the conditions needed for star formation. But why would this process affect red spirals differently than other galaxies? One hypothesis is that these galaxies might have formed in a unique environment that made them especially sensitive to black hole-driven changes. Perhaps they were born with just the right balance of gas and structure that allowed them to keep their spiral shape, while still shutting down their star-forming processes. Some astronomers have also proposed that red spirals could be relics of an earlier cosmic age, galaxies that formed under conditions that no longer exist in today's universe. If the early universe had different physical conditions, such as variations in the distribution of dark matter or the prevalence of certain types of cosmic radiation, these factors might have influenced the formation of galaxies in ways that are rare today. In this scenario, red spirals would be like fossils from a bygone era, offering a glimpse into a past stage of galactic evolution that no longer occurs naturally. This idea is difficult to test, but future observations of extremely distant galaxies might help determine whether red spirals were once more common in the past. The James Webb Space Telescope and other next-generation observatories are already beginning to provide new insights into the nature of galaxy formation. By looking at galaxies from billions of years ago, essentially peering back in time, we may be able to see whether red spirals were once more abundant. If they turn out to be common in the distant past, it would suggest that they represent an older stage of galaxy evolution that has mostly faded away. But if red spirals are just as rare in the early universe as they are today, then it would mean that whatever causes them is something highly specific, rather than a general phase in galaxy evolution. This would make them even more mysterious, as it would imply that their formation requires conditions that are not just rare but also stable over cosmic timescales. Ultimately, red spirals remind us that the universe is still full of surprises. Despite decades of studying galaxies, we continue to find anomalies that don't fit into our existing frameworks. Every time we think we have a clear picture of how the cosmos works, something like the mystery of red spirals comes along and forces us to rethink our assumptions. As our technology improves and our ability to analyze distant galaxies expands, we may one day solve the mystery of red spirals. But for now, they remain one of the strangest, most intriguing puzzles in astronomy. Are they a temporary stage in galaxy evolution, or a stable but rare type of galaxy? Are they shaped by external forces, or by internal processes we don't yet understand? And what do they tell us about the deeper, hidden mechanisms governing the structure of the universe? Until we have answers, the mystery of red spirals will continue to challenge our understanding of the cosmos. The more we study them, the more we realize that the universe still has secrets waiting to be uncovered. Perhaps one day, we will look back on red spirals not as an anomaly, but as a key piece of a much larger puzzle, one that could reshape our entire understanding of galaxies, dark matter, and the evolution of the universe itself. The mystery of red spirals is not just about classification, it's about the fundamental processes that shape galaxies over billions of years. If we can't fully explain why some galaxies turn red while keeping their spiral arms, then we might be missing a key piece of the puzzle in understanding galaxy evolution as a whole. Could it be that our models of how galaxies grow, change, and die are incomplete? Are we underestimating the role of certain cosmic forces? And what does this mean for the long-term future of the universe? One of the biggest questions surrounding red spirals is whether they represent a stable, long-term galactic form, or if they are simply in a transitional phase. If they are a transition between a spiral galaxy and an elliptical one, then studying them could give us insight into how galaxies transform over time. However, if red spirals are a stable, long-lasting type of galaxy, then they might represent an entirely different evolutionary path, one that has been overlooked until now. Astronomers have found that red spirals tend to be more massive than their blue counterparts. This suggests that their evolution might be linked to their size. Larger galaxies experience stronger gravitational forces, which can influence how they interact with their surroundings. Could it be that red spirals are the result of a specific type of interaction that only affects massive galaxies? Or is there something about their internal structure that makes them different from blue spirals? One way to investigate this is by looking at their rotation. Spiral galaxies rotate, and their speed of rotation can tell us a lot about their internal dynamics. If red spirals rotate differently than blue spirals, that might be a clue about why their star formation stopped. Some studies suggest that red spirals rotate more slowly than their blue counterparts, which could mean that their gas was used up or removed in a way that didn't disrupt their structure. But not all red spirals show this trend, meaning there might be multiple ways for a galaxy to become a red spiral. Another key factor is dark matter. Dark matter is an invisible form of matter that makes up most of the mass in the universe. It doesn't emit light, but its gravity shapes the structure of galaxies. If red spirals have a different distribution of dark matter than blue spirals, that could help explain why they behave differently. Some theories suggest that red spirals might have denser halos of dark matter, which could influence how they retain or lose gas. Another intriguing possibility is that red spirals are relics from an earlier stage of the universe. If conditions in the early universe were different, such as different levels of cosmic radiation or a different distribution of matter, then perhaps red spirals formed under those unique conditions and have remained unchanged ever since. In this scenario, there would be ancient fossils of a universe that no longer exists, preserving the imprint of an era when galaxy formation worked differently. Recent discoveries have also suggested that red spirals might be more common than previously thought. Initially, they were considered rare, but new telescopes and surveys have found them in greater numbers. This raises another question: are red spirals actually rare, or have we simply been looking in the wrong places? If they are more common than expected, that would mean they play a bigger role in galaxy evolution than we assumed. Some astronomers believe that environment plays a crucial role in shaping red spirals. Many red spirals are found in galaxy clusters, where interactions between galaxies are frequent. If a spiral galaxy falls into a cluster, it can experience a process called harassment, where gravitational interactions with other galaxies strip away its gas and shut down star formation. This could explain why some spirals turn red while keeping their structure. But not all red spirals are in clusters. Some exist in isolation, far from other galaxies. This suggests that internal processes, such as activity from a central supermassive black hole, might be shutting down star formation instead. If a black hole in the center of a galaxy suddenly becomes active, it can release powerful jets of energy that heat up or expel gas, preventing new stars from forming. One of the biggest challenges in understanding red spirals is that they don't fit neatly into any single category. Some seem to be fading remnants of once active blue spirals. Others seem to have been red for billions of years, suggesting they formed differently from the start. And some even show faint signs of star formation, meaning they aren't completely dead, but are evolving in ways we don't yet understand. The more we study red spirals, the more questions arise. Do they represent a missing link between spirals and ellipticals? Are they a stable but overlooked type of galaxy? Or are they the result of multiple, unrelated processes that happen to produce similar-looking galaxies? The answers to these questions could reshape our understanding of how galaxies evolve and interact with their surroundings. With new telescopes like the James Webb Space Telescope, we are getting closer to answering these questions. By looking at galaxies farther back in time, we might find evidence that red spirals were once more common. If we can trace their history, we might finally understand why they exist and what they tell us about the broader workings of the universe. For now, red spirals remain one of the strangest and most intriguing mysteries in astronomy. They challenge our assumptions about how galaxies work, and they remind us that the universe is far more complex than we ever imagined. Until we can fully explain them, they will continue to be a puzzle that drives astronomers to keep searching for answers. The mystery of red spirals is not just a minor curiosity, it forces us to rethink some of the fundamental ideas about galaxy evolution. When we look at the vast universe, we tend to categorize galaxies into clear groups: spirals, ellipticals, irregulars. But red spirals exist in a gray area, defying these simple classifications. If we don't understand why they exist, then we might be missing a crucial piece of the puzzle in how galaxies change over billions of years. Are they just a rare phenomenon, or do they represent an entire category of galaxies that has gone unnoticed? One of the leading theories behind red spirals is the role of quenching, a process that stops star formation in a galaxy. But why does quenching happen in some spirals while others remain blue and active for billions of years? There are many possible explanations, and each one brings us closer to understanding what makes red spirals unique. One possibility is that red spirals were once normal blue spirals, but something removed or heated their gas so much that they could no longer form new stars. This could happen through interactions with other galaxies. When galaxies pass close to each other, gravitational forces can pull away gas and disrupt star formation. This process, known as strangulation, could turn a blue spiral into a red one while leaving its structure intact. But there's a problem: many red spirals exist in isolation, far from other galaxies. If strangulation were the main cause, we wouldn't expect to find so many of them in empty space. Another possibility is that red spirals lost their star-forming ability due to feedback from their central supermassive black hole. In most large galaxies, there is a massive black hole at the center, millions or even billions of times the mass of the Sun. When these black holes become active, they release enormous amounts of energy in the form of radiation and jets of high-energy particles. This energy can heat up or expel gas from the galaxy, making it impossible for new stars to form. Some astronomers believe that this kind of AGN feedback, active galactic nucleus feedback, could be responsible for turning blue spirals into red spirals. If the black hole in the center of a spiral galaxy suddenly became highly active, it could shut down star formation permanently, leaving behind a red spiral. But even this explanation has complications. Not all red spirals show evidence of having an active black hole in the past. And some red spirals do have small amounts of ongoing star formation, meaning that whatever is shutting down their star formation isn't always a permanent process. This suggests that multiple mechanisms might be responsible for red spirals, rather than just one. One of the most intriguing aspects of red spirals is their location in the universe. Many of them exist in galaxy clusters, huge groups of galaxies bound together by gravity. In these environments, red spirals are often found on the outskirts of clusters, suggesting that their transformation from blue to red might be connected to their movement through these dense regions. As a spiral galaxy falls into a cluster, it moves through hot, ionized gas known as the intracluster medium. This gas can strip away the cooler star-forming gas inside the galaxy in a process called ram pressure stripping. The result? A spiral galaxy that still has its arms but can no longer form new stars, essentially a red spiral. But not all red spirals are found in clusters. Many exist in more isolated regions, raising another mystery. If they weren't transformed by interactions with other galaxies or clusters, then what caused them to stop forming stars? One possibility is that they simply ran out of gas naturally, either because they formed in an environment with little available gas or because they used up their reserves more quickly than other galaxies. If this is the case, then red spirals might not be a temporary phase at all. They could be a stable type of galaxy that has been overlooked until now. Another interesting discovery is that red spirals tend to be more massive than their blue counterparts. This suggests that mass plays a role in their transformation. Larger galaxies have stronger gravitational fields, which can make it harder for gas to escape. If a red spiral started out as a massive blue spiral, its gravity might have helped it hold onto its shape even after star formation stopped. In contrast, smaller galaxies that lose their gas tend to become ellipticals, because they don't have enough gravitational pull to keep their structure intact. Some astronomers have also noticed that red spirals tend to rotate more slowly than blue spirals. This raises another question. Did their rotations slow down as they aged, or were they always slower? If red spirals have always rotated more slowly, that could mean they formed differently from the start, rather than evolving from blue spirals. This would make red spirals an entirely separate type of galaxy rather than just a transitional phase. Another theory is that red spirals might be the remnants of ancient galaxies that formed early in the universe. In the early cosmos, conditions were different. Galaxies formed in an environment with higher radiation levels, different distributions of matter, and stronger cosmic winds. If red spirals formed under those conditions and remained relatively unchanged, then they could be ancient relics of a bygone era. In this scenario, red spirals would be like fossils, preserving the state of the universe as it was billions of years ago. One of the reasons red spirals remained a mystery for so long is that they were considered rare. Early surveys of galaxies mostly focused on large, bright objects, and red spirals didn't stand out as much as other galaxy types. But newer telescopes and surveys have found more of them, suggesting that they might be more common than previously thought. If they exist in greater numbers, that means they play a bigger role in galaxy evolution than we once believed. Ultimately, the mystery of red spirals is still unsolved. Are they a missing link between spirals and ellipticals? A stable but overlooked galaxy type? Or a sign that our understanding of galaxy evolution is incomplete? With new telescopes like the James Webb Space Telescope and upcoming galaxy surveys, we may finally get the answers we need. But for now, red spirals remain one of the strangest and most intriguing enigmas in the universe, challenging everything we thought we knew about how galaxies evolve. The deeper we look into the universe, the stranger red spirals become. If they were just an anomaly, an occasional misfit in galaxy classification, then they wouldn't be such a big deal. But the more astronomers study them, the clearer it becomes that they aren't just rare oddities. They could be a fundamental, yet overlooked, part of how galaxies evolve. If that's true, then we might need to rethink one of the biggest assumptions in astronomy, that galaxies move in a predictable cycle from young, blue, and full of new stars to old, red, and elliptical. Red spirals suggest that the story isn't that simple. A major question is whether red spirals are a transition phase or a final state. If they are just a temporary stage in galaxy evolution, that means we are catching them at a critical moment, after they have stopped forming stars but before they transform into something else. If that's the case, then red spirals might all eventually become elliptical galaxies, and we are just lucky enough to be seeing them in the middle of that process. But if red spirals are a permanent galaxy type, that means there could be something fundamentally different about them, something that stops them from ever becoming elliptical while also preventing them from staying blue. One of the most perplexing things about red spirals is their structure. Normally, when a galaxy stops forming stars, its shape starts to change. Blue spirals, which have active star formation, tend to have well-defined arms and a flattened disk. But over time, if star formation stops, the galaxy should lose its structure. The arms should fade, the disk should puff up, and the whole thing should start looking more like a featureless elliptical galaxy. But red spirals don't do that. Even though they have lost most of their star formation, they keep their shape. This is why astronomers are so confused. If they followed the normal rules of galaxy evolution, red spirals shouldn't exist at all. This suggests that whatever is stopping star formation in red spirals isn't the same thing that turns other galaxies into ellipticals. Something is keeping these galaxies in their spiral shape long after they should have lost it. But what? One theory is that they might still have a thin layer of cold gas left, just enough to keep their structure intact, but not enough to form new stars. If this is true, then red spirals might not be entirely dead galaxies. They might be galaxies that are just barely hanging on, with enough structure left to keep their spiral arms from fading away. Another possible explanation is the role of dark matter. We still don't fully understand how dark matter affects galaxies, but we do know that it plays a crucial role in their evolution. Dark matter is an invisible form of mass that surrounds galaxies, holding them together through gravity. Some researchers think that red spirals might have an unusually high concentration of dark matter compared to other spirals. If this is true, then their dark matter halos might be keeping them from collapsing into ellipticals, even though they have stopped forming new stars. This would mean that red spirals are actually galaxies that are being held together by invisible forces, preventing them from evolving in the way we would expect. A key piece of evidence for this theory comes from how red spirals rotate. Observations show that they spin differently than normal blue spirals. In general, galaxies rotate because of the balance between gravity and the movement of their stars and gas. But red spirals have been found to rotate in ways that don't quite match up with our models. Some spin slower than expected, while others seem to have unusual motion patterns that suggest something unseen is affecting them. If dark matter is playing a stronger role in red spirals than in other galaxies, that could explain why they are so different. Then there's the question of age. How long have red spirals existed? Are they a recent phenomenon, or have they been around for billions of years? To answer this, astronomers look at the age of the stars inside them. By analyzing the light from a red spiral, we can estimate when its stars were formed. What we find is surprising. Many red spirals have very old stars, some dating back to the early universe. This means that these galaxies must have stopped forming stars a long time ago. But if that's true, then why do they still have their spiral shape? Why haven't they collapsed into ellipticals like we would expect? One possible answer is that red spirals formed differently from the very beginning. Maybe they weren't always blue spirals that turned red, but instead, they have always been a separate category of galaxy. If that's the case, then our classification of galaxies has been missing an entire type this whole time. Instead of thinking of galaxies as either spirals or ellipticals, we might need to add a third major category: long-lived, non-star-forming spirals. This idea is controversial because it challenges a lot of what we thought we knew. It suggests that some galaxies don't follow the usual rules of star formation and evolution. Instead of being part of a predictable cycle, red spirals might be galaxies that formed under very specific conditions and never changed. If this is true, then studying them could help us understand not just how galaxies evolve, but also what conditions in the early universe were like. Some researchers think red spirals might be connected to a mysterious population of galaxies known as quench spirals. These are galaxies that, for some reason, suddenly stopped forming stars long before they should have. Normally, galaxies run out of star-forming gas slowly over billions of years. But quench spirals seem to have shut down their star formation almost instantly. If red spirals are related to them, then that means something dramatic must have happened to shut them down so quickly. One theory is that a massive burst of energy from their central black holes could have done it. If the black hole at the center of a galaxy suddenly released a huge amount of energy, it could heat up or expel all the gas in the galaxy, making it impossible for new stars to form. This is called AGN feedback, and it has been observed in other galaxies before. If red spirals went through this kind of event in the past, that could explain why they are no longer forming stars. But it still doesn't explain why they kept their shape. Another possibility is that red spirals were affected by interactions with dark matter filaments. The universe is structured like a vast cosmic web, with galaxies forming along invisible filaments of dark matter. If red spirals formed in a region where these filaments are especially dense, they might have experienced forces that other galaxies didn't. This could have affected their ability to form stars while still keeping their spiral shape intact. Ultimately, the mystery of red spirals remains unsolved. They challenge everything we thought we knew about how galaxies evolve, and they suggest that the universe is far more complex than we ever imagined. Are they a missing link between spirals and ellipticals? A completely separate type of galaxy? A sign that our understanding of dark matter is incomplete? With new telescopes and better technology, we may finally get the answers we need. But for now, red spirals remain one of the strangest, most fascinating, and most unexplained phenomena in the universe. The existence of red spirals raises an even deeper question: how many of them are out there? Are they truly rare, or have we just been overlooking them because they don't fit into our traditional categories? This is where large-scale sky surveys have been incredibly useful. Projects like the Sloan Digital Sky Survey (SDSS) have mapped millions of galaxies across the universe, giving us a much broader sample to analyze. When astronomers combed through this data, they found something surprising: red spirals aren't as rare as we once thought. They are uncommon, yes, but not unheard of. In fact, they may make up a significant fraction of all galaxies, especially in regions where galaxies are closely packed together. This raises another big question: do red spirals form in isolation, or are they the result of interactions with other galaxies? One clue comes from their locations. Studies have shown that red spirals are more likely to be found in dense environments, such as galaxy clusters. This suggests that they might have been affected by their surroundings. Perhaps they were once normal, blue, star-forming spirals, but something in their environment stripped them of their gas and stopped them from forming new stars. This process, known as environmental quenching, happens when a galaxy moves through a cluster and loses its star-forming material due to interactions with other galaxies or hot gas in the cluster. One way this can happen is through a process called ram pressure stripping. When a galaxy moves through a cluster, it encounters hot gas that fills the space between galaxies. If the pressure from this gas is strong enough, it can strip away the galaxy's own gas, cutting off its ability to form new stars. This could explain why red spirals are found in clusters. Perhaps they were once normal blue spirals, but as they moved through the cluster, they lost their gas and turned red. However, there's a problem with this idea. Ram pressure stripping is usually very violent, and it often distorts a galaxy's shape. If red spirals were affected by this process, we would expect them to look more chaotic or irregular. Instead, they maintain their beautiful, well-defined spiral arms, which suggests that something else might be going on. Another possibility is that red spirals formed as a result of galaxy mergers. When two galaxies collide, their gas can be disrupted, leading to a burst of star formation followed by a period of quiescence. If a spiral galaxy merged with another galaxy in just the right way, it might lose its ability to form new stars while still keeping its structure intact. This would make red spirals the remnants of past galaxy interactions, ghosts of cosmic collisions that happened millions or even billions of years ago. But not all red spirals are found in clusters. Some exist in much quieter environments, far away from other galaxies. This suggests that there might be multiple ways for a spiral galaxy to turn red. In isolated cases, internal factors could play a bigger role. Perhaps these galaxies used up their gas naturally and simply ran out of fuel for star formation. If that's true, then red spirals could represent a completely normal, yet rarely observed, stage of galaxy evolution. Another hypothesis is that red spirals are being affected by a process known as AGN feedback. At the center of almost every galaxy lies a supermassive black hole. In some galaxies, these black holes are actively consuming matter, releasing massive amounts of energy in the process. This energy can heat up or expel the gas in a galaxy, preventing it from forming new stars. If the black hole in a red spiral became active at some point in the past, it might have shut down star formation, while leaving the spiral structure intact. Some red spirals do show evidence of past black hole activity, lending some support to this idea. But even if AGN feedback is part of the story, it doesn't explain everything. Why do some galaxies undergo this process while others don't? Why do red spirals keep their shape instead of transforming into ellipticals? These questions remain open, and answering them could change our understanding of how galaxies evolve. One of the most puzzling aspects of red spirals is their motion. When astronomers study how these galaxies rotate, they find unexpected patterns. In some cases, the outer edges of red spirals rotate more slowly than we would expect, suggesting that something is affecting their dynamics. This could be another clue that dark matter plays a role. If red spirals have an unusual distribution of dark matter, it might explain both their structure and their unexpected motion. Some researchers have even speculated that red spirals could be evidence of exotic new physics. Could they be affected by modifications to gravity that we don't yet understand? Could they be linked to unknown properties of dark matter? These are extreme possibilities, but red spirals are strange enough that they force us to consider all possibilities, even ones that challenge our current models of the universe. As telescope technology improves, we are beginning to study red spirals in greater detail than ever before. Future telescopes like the Vera C. Rubin Observatory and the James Webb Space Telescope will allow us to analyze these galaxies with unprecedented precision. By looking deeper into their structure, measuring their gas content, and studying their histories, we may finally begin to unravel the mystery. One of the most exciting prospects is the possibility that red spirals could help us understand the distant past. Because light takes time to travel across the universe, looking at distant galaxies is like looking back in time. If we can find ancient red spirals in the early universe, we might be able to piece together how they formed and what role they play in galaxy evolution. For now, red spirals remain an enigma, one of the biggest unresolved questions in astronomy. They defy our expectations, challenge our models, and hint at hidden forces shaping the universe. They are a reminder that even in a time of incredible scientific progress, the cosmos still holds secrets waiting to be uncovered. Red spirals challenge one of the most fundamental ideas in galaxy classification, the notion that galaxies follow a predictable life cycle. Traditionally, astronomers have categorized galaxies into two broad types: blue, star-forming spirals, and red, inactive ellipticals. This classification, often visualized as the Hubble sequence, suggests a natural progression in galaxy evolution. A galaxy starts as a young, gas-rich spiral, forms stars for billions of years, and eventually exhausts its gas, transforming into a red elliptical. However, red spirals defy this neat classification. They exist in a strange middle ground, retaining the structure of young, active galaxies while exhibiting the characteristics of older, inactive ones. This raises a crucial question. Are red spirals a transitional phase in galaxy evolution, or are they something entirely different? To answer this, astronomers have turned to simulations. By creating virtual models of galaxies and evolving them over billions of years, researchers can test different scenarios to see if red spirals emerge naturally. Some simulations suggest that red spirals could form when a galaxy undergoes a sudden loss of gas without experiencing a major disruption. This could happen if a galaxy's gas is slowly stripped away by a nearby galaxy cluster, or if internal processes, such as an outburst from a central supermassive black hole, expel the gas outward, shutting down star formation. However, these models still struggle to explain why red spirals retain their structure for so long. Without active star formation, spiral arms should gradually fade away, leaving behind a more featureless shape. Yet, red spirals persist, their arms still well-defined despite the lack of new stars. Another approach is to study individual red spirals in extreme detail. By analyzing their chemical composition, scientists can determine when their last bursts of star formation occurred. Some red spirals appear to have stopped forming stars relatively recently, within the last few 100 million years, while others have been dormant for billions of years. This suggests that there isn't just one way to become a red spiral. Some may have shut down gradually, while others may have undergone a more sudden transformation. The presence of old and young red spirals complicates the picture, making it difficult to pinpoint a single explanation. One intriguing clue comes from the way red spirals interact with their surroundings. Unlike their blue counterparts, red spirals tend to have fewer satellite galaxies. This is unusual because spiral galaxies typically have a population of smaller galaxies orbiting them, some of which eventually merge with the larger galaxy. If red spirals have fewer satellites, this could mean that they formed in a different way, or that they actively repel smaller galaxies. One possibility is that red spirals have already consumed or ejected many of their satellite galaxies, leaving them relatively isolated. Another idea is that their environment has played a key role in shaping them. If a red spiral formed in a region with very few neighboring galaxies, it might have evolved differently than typical spirals, avoiding the mergers and interactions that usually shape galaxy evolution. Dark matter could also be playing a role. Every galaxy is thought to be surrounded by a vast, invisible halo of dark matter, which helps to hold it together. Some red spirals appear to have more massive dark matter halos than typical spirals, suggesting that they might have formed in regions of space where dark matter is particularly dense. If a galaxy formed in a deep gravitational well of dark matter, it might have experienced different evolutionary pressures than a normal spiral, leading it to lose its gas while still retaining its structure. This could also explain why some red spirals show unusual rotation curves. If their dark matter is distributed differently, it could be affecting their motion in unexpected ways. Some researchers have proposed an even more radical idea. What if red spirals are not a phase in galaxy evolution, but a completely separate type of galaxy that formed differently from the beginning? If this is the case, then red spirals might not be failed spirals or dying ellipticals, but rather a unique and stable category of galaxies that we have simply overlooked. This idea would require a fundamental rethink of how galaxies form and evolve, but it is not entirely implausible. After all, our understanding of galaxies is constantly evolving, and discoveries like red spirals remind us that the universe is often more complex than our models suggest. Future observations will be key to solving this mystery. The next generation of telescopes will allow us to study red spirals in more detail than ever before. The Vera C. Rubin Observatory, for example, will conduct a massive survey of the night sky, capturing images of billions of galaxies. This will help astronomers identify more red spirals, allowing them to study their properties across different environments. Meanwhile, the James Webb Space Telescope, JWST, is already providing new insights into galaxy evolution by peering deep into the cosmos with its infrared vision. If JWST finds red spirals in the early universe, it could provide crucial clues about their origins. Another exciting possibility is using gravitational lensing to study red spirals. Gravitational lensing occurs when a massive object, like a galaxy cluster, bends the light from more distant galaxies, magnifying them like a cosmic telescope. If we can find lensed red spirals, we can study them in much greater detail, potentially revealing new information about their structure and history. Ultimately, the mystery of red spirals is far from solved. They challenge our understanding of galaxy evolution, forcing us to reconsider what we thought we knew about how galaxies form, change, and die. Whether they are a transitional phase, the result of unique environmental conditions, or an entirely new class of galaxies, one thing is certain: red spirals are a cosmic anomaly that refuses to fit neatly into our existing models. And in science, anomalies are often where the biggest breakthroughs happen. As we continue to explore the universe, red spirals serve as a reminder that there is still so much we don't understand. They are cosmic puzzles waiting to be solved, and with each new discovery, we move one step closer to unlocking their secrets. Red spirals are not just rare cosmic anomalies. They represent a deeper challenge to our understanding of how galaxies evolve over billions of years. One of the most perplexing aspects of these galaxies is their ability to maintain their spiral structure despite the lack of active star formation. Normally, spiral arms are thought to be sustained by density waves, patterns in the galaxy's disk that compress gas and trigger new star formation as they move through the galaxy. But in red spirals, star formation has mostly shut down. This raises a major question. If there are no new stars being formed, what is keeping these spirals intact? One possible explanation is that red spirals have unusually stable disk dynamics. In other words, the stars within them might be moving in such a way that prevents the arms from dissolving into a more chaotic structure. In most galaxies, interactions with other galaxies, bursts of star formation, or internal gravitational disturbances can gradually disrupt the spiral pattern. However, red spirals appear to have avoided these disruptions. This suggests that whatever process shut down their star formation did so without disturbing their overall structure. One idea is that red spirals are the remnants of galaxies that used to be part of clusters but were ejected due to gravitational interactions. In dense galaxy clusters, galaxies are constantly interacting with each other, and the hot gas that fills the space between them. This environment can strip a galaxy of its gas, halting star formation and turning it red. If a spiral galaxy lost its gas in a cluster and was then flung out into intergalactic space, it could become a red spiral, isolated from other galaxies and no longer undergoing disruptive interactions. This could explain why some red spirals appear to be more isolated than typical spirals. Another intriguing clue comes from studying the mass distribution within red spirals. Observations suggest that some red spirals have more massive central bulges than typical blue spirals. This might mean that their transformation into red spirals was linked to an event that caused material to fall into their centers, increasing the density of stars in the core while shutting down star formation in the outer disk. One way this could happen is through minor mergers, smaller galaxies falling into the red spiral, adding to its central bulge while not disturbing its overall structure. If these mergers were gas-poor, they wouldn't reignite star formation, but they could help explain why red spirals have more prominent bulges. Supermassive black holes at the centers of red spirals may also play a crucial role in their evolution. Every large galaxy is thought to harbor a supermassive black hole at its center, and in many cases, these black holes can influence the entire galaxy. When a black hole is actively feeding on surrounding gas, it releases enormous amounts of energy in the form of radiation and high-speed particles. This process, known as AGN feedback, active galactic nucleus feedback, can heat up or even blow away the gas in the galaxy, effectively shutting down star formation. Some red spirals show evidence of past AGN activity, suggesting that their black holes may have been responsible for cutting off their ability to form new stars. One of the most exciting aspects of studying red spirals is that they might offer a glimpse into the future of our own Milky Way. The Milky Way is currently a blue, star-forming spiral galaxy, but it won't remain that way forever. In a few billion years, it will collide with the neighboring Andromeda galaxy, likely merging into a larger elliptical galaxy. However, Before that happens, it's possible that the Milky Way could go through a phase where it resembles a red spiral. If internal processes or interactions with satellite galaxies shut down its star formation before it fully merges with Andromeda, the Milky Way could become a red spiral for a time before eventually transforming into something else. Understanding red spirals is not just about solving one cosmic mystery, it's about refining our entire picture of galaxy evolution. If red spirals turn out to be a common but previously overlooked phase in galaxy life cycles, it could mean that our current models of galaxy evolution are missing a crucial piece of the puzzle. The discovery of red spirals is also a testament to the power of modern astronomical surveys. For much of the 20th century, galaxies were classified based on small samples observed through telescopes that could only study a handful at a time. But today, massive surveys like the Sloan Digital Sky Survey (SDSS) have mapped millions of galaxies, revealing patterns and anomalies that astronomers never expected. Red spirals were once considered an oddity, but thanks to these large datasets, we now know they are more common than previously thought. The next steps in unraveling the mystery of red spirals will likely come from even more advanced observations. The James Webb Space Telescope is already providing unprecedented views of distant galaxies, allowing astronomers to see the earliest stages of galaxy formation. If JWST finds red spirals in the early universe, it would suggest that these galaxies are not just a late-stage phenomenon but something fundamental to galaxy evolution. Another promising approach is to use radio telescopes to study the remaining gas in red spirals. Even though these galaxies appear to have stopped forming stars, they might still contain cold gas that is difficult to detect with optical telescopes. If red spirals are found to have hidden gas reservoirs, it could mean that something is preventing this gas from forming stars, which would be a key clue in solving the mystery. As astronomers continue to gather data, red spirals remain a fascinating enigma. They challenge our assumptions about galaxy evolution, raise new questions about the role of environment and internal processes, and hint at a more complex picture of how galaxies change over time. One thing is certain: every new discovery about red spirals brings us closer to understanding the intricate dance of matter, gravity, and time that shapes the cosmos. They are a reminder that even in a universe as vast as ours, there are still surprises waiting to be uncovered. The mystery of red spirals continues to deepen as astronomers uncover new details about their structure, history, and potential evolutionary pathways. One of the most perplexing aspects of these galaxies is their apparent ability to maintain a spiral shape while lacking the key ingredient that typically defines spiral galaxies: ongoing star formation. Traditional spiral galaxies are vibrant, with young, hot stars illuminating their arms in a striking blue hue. But red spirals defy this expectation, exhibiting a structure that should belong to an active, evolving galaxy while displaying the red, aged glow of an inactive one. This contradiction suggests that red spirals might be caught in a transitional phase, moving from one category of galaxies to another. However, if this transition were a rapid one, we would expect to see very few of them. Instead, red spirals are more common than previously thought, which implies that whatever process is keeping them in this state is long-lasting and stable. One possibility is that these galaxies have undergone strangulation, a process in which a galaxy's ability to acquire new gas is slowly cut off. Without a fresh supply of gas to form new stars, a galaxy would gradually fade from blue to red over time. But strangulation alone doesn't explain why the galaxy remains a spiral. In most cases, when a galaxy stops forming stars, it begins to lose its defined structure, becoming more diffuse or even evolving into an elliptical shape. The fact that red spirals keep their arms suggests that whatever halted their star formation did so in a way that preserved their overall structure. A leading theory is that red spirals have undergone a process known as gentle quenching. Instead of experiencing a violent event that disrupts their shape, such as a major merger with another galaxy, these galaxies may have simply run out of the necessary conditions for star formation. This could happen if their gas was gradually heated to temperatures too high for it to collapse into new stars. The presence of an active galactic nucleus, AGN, or other internal heating mechanisms could explain this. If a supermassive black hole at the center of a red spiral went through a phase of intense activity, it could have released enough energy to heat the surrounding gas and prevent it from cooling down and forming new stars. Observations of red spirals suggest that they are more common in certain environments. While they are not as frequently found in dense galaxy clusters, where interactions with other galaxies can strip away gas, they do appear in intermediate density regions. These are areas where galaxies are close enough to influence one another but not so close that they constantly collide. This suggests that mild interactions with neighboring galaxies could play a role in their transformation. Another key clue comes from their rotation curves. Studies show that red spirals rotate similarly to their blue counterparts, meaning that the gravitational forces shaping their structures have remained stable despite the cessation of star formation. This supports the idea that these galaxies have avoided major disruptive events while still undergoing significant internal changes. The existence of red spirals also raises questions about the role of dark matter. Dark matter is thought to play a crucial role in maintaining the structure of galaxies by providing the extra gravitational pull needed to hold them together. If red spirals have an unusually high concentration of dark matter, this could help explain why they retain their shape despite no longer forming new stars. Future studies using advanced telescopes and gravitational lensing techniques may help reveal whether red spirals have unique dark matter distributions that set them apart from other galaxies. As astronomers continue to study red spirals, they are also using computer simulations to model their evolution. By creating virtual galaxies and subjecting them to different environmental conditions, researchers can test various scenarios to see which best reproduces the characteristics of red spirals. Early results suggest that these galaxies may have formed in a more gas-rich environment, but later experienced a shift that cut off their supply of new material. This could mean that red spirals are an important missing link in our understanding of galaxy evolution, showing what happens in the intermediate stages between star-forming spirals and fully quenched elliptical galaxies. Another fascinating aspect of red spirals is the possibility that some of them could reignite star formation under the right conditions. If a red spiral were to encounter a fresh supply of gas, perhaps by merging with a smaller, gas-rich galaxy, it could potentially begin forming new stars again, shifting back toward a blue spiral state. However, observations suggest that most red spirals remain in their quenched state for extended periods, meaning that whatever process shut them down is strong enough to prevent easy reactivation. The deeper we look into the cosmos, the more red spirals we find, and each new discovery adds another piece to the puzzle. These galaxies challenge our understanding of how galaxies live and die, proving that the universe is far more complex than we once thought. The study of red spirals is still in its early stages, but one thing is clear: these galaxies are rewriting the rules of galactic evolution. As future telescopes come online, such as the Vera C. Rubin Observatory and the European Extremely Large Telescope, we will gain even more detailed insights into the history and fate of red spirals. These next-generation observatories will allow astronomers to peer deeper into their structures, analyze their chemical compositions, and track their movement over time. By doing so, we may finally uncover the full story of these mysterious galaxies and understand their place in the grand cosmic narrative. Red spirals remain an unsolved mystery, but their presence challenges our assumptions about how galaxies evolve. Traditionally, galaxies were thought to follow a clear path. Spiral galaxies are active and star-forming, while elliptical galaxies are old and passive. Red spirals defy this expectation, sitting in an unexpected middle ground. They look like they should be alive, yet their colors tell us they are fading. This contradiction suggests that galaxy evolution is far more complex than a simple binary between active and inactive galaxies. One of the biggest questions surrounding red spirals is whether they represent a temporary stage or a permanent classification. Are they galaxies that are slowly evolving into something else, or do they remain in this red spiral state indefinitely? If they are transitioning, what are they transitioning into? If they are a long-lasting category, why aren't they more common? The more we study them, the more it seems like they don't fit neatly into any single evolutionary pathway. One key aspect of red spirals that scientists are investigating is their star formation history. Although they appear to have shut down new star formation, there is evidence that some of them may have formed stars in the relatively recent past. This suggests that the process that turned them red wasn't an instant shutdown, but rather a gradual decline. The question is, what caused this decline? Was it an internal process, like a supermassive black hole heating up its surroundings and shutting down star formation? Or was it an external factor, like interactions with nearby galaxies stripping away their gas? The role of galactic mergers is another factor being explored. While major galaxy mergers often result in the complete disruption of a spiral structure, leading to the formation of an elliptical galaxy, minor mergers could have different effects. A small, gas-poor galaxy merging with a larger spiral could potentially trigger enough turbulence to disrupt star formation without completely destroying the spiral shape. This would leave behind a galaxy that still looks like a spiral but no longer has the ability to form new stars, effectively turning it into a red spiral. Another possibility is that red spirals could have formed differently from the start. Instead of being blue spirals that turned red, could they have always been in a low star formation state? If so, this would challenge the idea that all spiral galaxies begin their lives as active star-forming galaxies. Perhaps some galaxies were born in environments where star formation was never particularly strong, and they simply remained in a low-energy state for their entire existence. One of the most puzzling aspects of red spirals is their distribution in the universe. They are more commonly found in intermediate density regions, areas where galaxies are close enough to interact but not so close that they are constantly colliding. This suggests that their transformation may be linked to environmental factors. If a galaxy is in a region where it experiences mild gravitational interactions but not full-scale mergers, it could slowly lose its ability to form stars while still retaining its structure. Another possible explanation involves feedback from active galactic nuclei, AGN. When a supermassive black hole at the center of a galaxy goes through a highly active phase, it can release enormous amounts of energy. This energy can heat up the surrounding gas, preventing it from cooling and forming new stars. If a red spiral had a period of intense AGN activity in the past, this could explain why its star formation shut down while its structure remained intact. The challenge with this theory is that not all red spirals show signs of past AGN activity, so this may only be part of the story. As we develop better telescopes and analysis techniques, scientists are beginning to look at red spirals in more detail than ever before. Advanced simulations allow researchers to model different evolutionary scenarios to see which best match the characteristics of observed red spirals. These simulations suggest that red spirals might not have a single cause. Different galaxies may have become red spirals through different processes. Some may have experienced slow strangulation, others may have been affected by AGN feedback, and some may have had unusual formation histories. One of the key ways to test these theories is by examining the chemical composition of red spirals. The elements present in a galaxy's stars can tell us a lot about its history. If red spirals contain unusually high amounts of certain heavy elements, this could indicate that they went through a period of rapid star formation before shutting down. On the other hand, if their elemental composition is similar to that of normal blue spirals, this could suggest that they simply lost their ability to form new stars without any dramatic bursts of activity. Red spirals may also offer insights into the broader picture of galaxy evolution. If they truly represent an intermediate stage between star-forming spirals and fully quenched ellipticals, they could help us understand how galaxies change over time. But if they turn out to be a long-lived, stable category, this would force us to rethink our models of how galaxies work. Either way, studying them will provide valuable clues about the forces that shape the universe. One of the biggest challenges in studying red spirals is that they are relatively rare compared to blue spirals and elliptical galaxies. This means that finding enough of them to draw firm conclusions requires surveying large portions of the sky. Upcoming projects like the Vera C. Rubin Observatory's Legacy Survey of Space and Time, LSST, will help with this by providing an unprecedented amount of data on galaxies across the universe. With these new observations, we may finally be able to answer some of the biggest questions about red spirals. As we continue to investigate these enigmatic galaxies, we must remain open to the possibility that they could reshape our understanding of cosmic evolution. The more we learn about them, the clearer it becomes that they are not just a minor anomaly but a fundamental piece of the puzzle. Whether they are a brief phase in a galaxy's life or a stable category of their own, red spirals challenge us to rethink what we thought we knew about galaxies. Ultimately, the mystery of red spirals reminds us that the universe is still full of surprises. Every time we think we have a complete picture of how galaxies work, we discover something that forces us to ask new questions. As new telescopes come online and our ability to explore the cosmos improves, we may finally unlock the secrets of red spirals. But for now, they remain one of the most intriguing and least understood phenomena in astrophysics. The mystery of red spirals continues to perplex astronomers, and as more data becomes available, the complexity of the problem only deepens. One of the major questions that scientists are trying to answer is whether red spirals are merely a transitional phase or if they represent a distinct, long-term evolutionary path. If they are transitioning, what are they transitioning into? And if they are a stable category, why aren't they more widely recognized in galaxy classification models? To address these questions, astronomers have turned to advanced simulations. These simulations allow researchers to model various evolutionary scenarios and compare them to the real-world observations of red spirals. By adjusting factors like star formation rates, gas supply, and interactions with other galaxies, scientists can test different hypotheses about what causes a spiral galaxy to turn red while still retaining its structure. One of the most compelling theories involves the gradual strangulation of star formation. Galaxies need cold gas to form new stars, and if something cuts off the supply of this gas, star formation will slowly decline. Unlike an abrupt event, such as a major collision or a sudden burst of energy from an active galactic nucleus, strangulation is a slow process. A galaxy that experiences strangulation may continue forming stars for a while, but as the last reserves of gas are used up, it will transition into a red spiral. This process could be caused by several factors. A galaxy in a region of space with fewer interactions may struggle to replenish its gas supply. If it drifts into an area with slightly denser intergalactic medium, its gas may be stripped away over time. Alternatively, internal processes, such as the activity of a supermassive black hole at the galaxy's center, could slowly heat the remaining gas, making it impossible for new stars to form. Another theory involves galaxy interactions on a smaller scale. Major galaxy mergers often result in the formation of elliptical galaxies, but smaller interactions, known as minor mergers, may have a different effect. If a red spiral was once a blue spiral that merged with a small gas-poor galaxy, the interaction could have disturbed its internal structure just enough to shut down star formation while preserving its spiral shape. These minor mergers may also introduce turbulence in the gas, preventing it from cooling and forming new stars. One of the biggest pieces of evidence supporting the minor merger theory is the discovery of red spirals with signs of past interactions. Some red spirals have been observed with tidal tails, elongated streams of stars and gas that suggest a past gravitational disturbance. This hints that a smaller galaxy may have passed through or merged with the spiral, causing changes that led to the loss of star-forming activity. But even if mergers and interactions play a role, they may not be the sole explanation. Some red spirals appear to have had no recent interactions at all. This suggests that multiple pathways could lead to the same outcome, and red spirals might not have a single cause. Instead, different galaxies may have turned red in different ways. Another critical question is whether red spirals can be found in all environments, or if they are more common in specific regions of space. Studies suggest that red spirals are more frequently found in intermediate density environments, places where galaxies are close enough to interact but not so tightly packed that they are constantly colliding. This observation supports the idea that red spirals could be the result of mild environmental effects rather than dramatic, high-impact events. The chemical composition of red spirals also provides crucial clues. The elements found in a galaxy's stars can tell scientists a lot about its past. If a red spiral contains high amounts of heavy elements, this could indicate that it once had a period of rapid star formation before shutting down. On the other hand, if its chemical makeup is more like that of blue spirals, this could suggest that it simply lost its ability to form stars gradually, without any sudden bursts of activity. One particularly interesting aspect of red spirals is that they challenge the traditional idea of the star formation. Main sequence. In astronomy, galaxies are often divided into two main groups: actively star-forming galaxies, which are typically blue, and passive galaxies, which are usually red. But red spirals don't fit neatly into either category. They have the structure of active galaxies but the color of inactive ones. This has led some astronomers to question whether our current classification system is too simplistic and whether red spirals represent an entirely separate category that needs to be acknowledged. Another factor that could play a role in the mystery is dark matter. While dark matter is invisible and doesn't interact with light in the same way normal matter does, it exerts a gravitational influence on galaxies. Some researchers speculate that differences in the distribution of dark matter could affect the evolution of red spirals. If a galaxy has an unusually high concentration of dark matter, this could alter its ability to hold on to gas and regulate star formation. However, this is still a largely unexplored area, and more research is needed to determine whether dark matter has any direct impact on the existence of red spirals. Future telescopes and observation projects will likely provide more answers. The Vera C. Rubin Observatory, set to begin full operation soon, will conduct an extensive sky survey that will include millions of galaxies. This will give scientists an unprecedented amount of data on red spirals, allowing them to compare their properties across different environments and evolutionary stages. Similarly, the James Webb Space Telescope, JWST, is already providing new insights into galaxy evolution by capturing incredibly detailed images of distant galaxies. By studying red spirals in more detail, JWST could help unravel some of the biggest mysteries surrounding their formation and fate. Despite all these efforts, red spirals remain an enigma. They defy expectations, sit outside traditional classification models, and challenge our understanding of how galaxies evolve. Are they the remnants of once active galaxies, slowly fading away? Are they evidence of a hidden force shaping the cosmos? Or do they represent an entirely new kind of galaxy, one that has yet to be fully understood? What makes the mystery even more compelling is that red spirals might be more common than we think. Many of them could be hiding in plain sight, overlooked due to biases in how we classify galaxies. As new data comes in, it's possible that what we now see as a rare anomaly could turn out to be a fundamental part of galaxy evolution. If we do eventually solve the mystery of red spirals, it won't just be an answer to one isolated question. It will be a window into the deeper workings of the universe. Every galaxy tells a story, and red spirals are telling us something that we don't yet fully understand. The question is, will we be able to listen closely enough to uncover the truth? The search for answers about red spirals isn't just about understanding a single type of galaxy. It's about redefining how we see the universe. For decades, astronomers have built models of galaxy evolution based on what we thought were clear patterns: blue, star-forming spirals transition into red, passive ellipticals through well-understood processes. But red spirals break that mold. They suggest that the journey from one stage to another isn't always as straightforward as we assumed. One of the biggest revelations in recent years is that red spirals aren't as rare as previously believed. Early surveys may have overlooked them simply because they didn't fit into existing classification systems. But as telescopes have improved, and as more sophisticated galaxy surveys have been conducted, it has become clear that red spirals make up a significant portion of the galactic population. The Sloan Digital Sky Survey (SDSS) has played a crucial role in identifying these galaxies, providing vast amounts of data that astronomers are still analyzing today. A major breakthrough came when researchers realized that many red spirals exist in a kind of cosmic middle ground. They aren't found in the densest galaxy clusters, where interactions are so extreme that spiral structures tend to be destroyed, nor are they as common in the most isolated regions of space, where galaxies can continue forming stars for billions of years without disruption. Instead, they appear in environments where interactions are just frequent enough to influence their evolution, but not enough to completely strip them of their structure. One possible explanation for their existence involves a process known as harassment. This occurs when a galaxy experiences multiple weak gravitational interactions over time rather than a single, dramatic collision. These interactions can gradually disturb the gas inside the galaxy, preventing it from forming new stars. Unlike major mergers, which can trigger bursts of star formation or lead to the formation of elliptical galaxies, harassment works more subtly. Over millions or even billions of years, it can slowly push a galaxy from the blue, star-forming category into the red, passive category without fundamentally changing its shape. Another possible factor is the presence of active galactic nuclei (AGN). At the center of many galaxies lies a supermassive black hole, and in some cases, these black holes can become active, spewing out enormous amounts of energy. This energy can heat up or even expel gas from the galaxy, shutting down star formation in a process known as AGN feedback. Some red spirals show signs that their central black holes may have played a role in their transformation, but whether this is the primary mechanism or just one piece of the puzzle remains unclear. Observations of red spirals also raise questions about the role of cosmic filaments, vast structures that connect galaxies across the universe. Some researchers suspect that the location of a galaxy within these filaments could influence its evolution. Galaxies that sit in dense parts of filaments may experience slow but consistent gas loss, leading to a gradual shutdown of star formation while still maintaining their spiral shape. But if red spirals are just galaxies in transition, why do some of them seem to remain in this state for billions of years? That's one of the most puzzling aspects of this mystery. If they were simply on their way to becoming elliptical galaxies, we would expect to see more of them actively changing shape. Instead, some red spirals appear to be stable, existing in a kind of limbo between blue spirals and ellipticals. This suggests that, for at least some galaxies, being a red spiral isn't a temporary phase, it's a long-term identity. Further complicating things is the fact that red spirals vary widely in their properties. Some still have small pockets of star formation, while others seem completely dormant. Some have tightly wound spiral arms, while others are more loosely structured. This suggests that there may not be a single explanation for red spirals, but rather a range of different processes that can lead to the same outcome. Another key question is whether red spirals have always existed in significant numbers or if they are more common in certain cosmic eras. Some researchers are investigating whether there were more red spirals in the early universe, which could provide clues about their long-term fate. If red spirals were more common billions of years ago, it might suggest that they are slowly fading away over time. But if they exist in roughly the same numbers throughout cosmic history, that would indicate that they are a more stable phenomenon. Looking ahead, upcoming telescopes and space missions will be crucial in solving this mystery. The James Webb Space Telescope, with its ability to peer deep into the past, may reveal whether red spirals were once more abundant. Meanwhile, projects like the Vera C. Rubin Observatory's Legacy Survey of Space and Time, LSST, will provide unprecedented detail on the structure and distribution of these galaxies. Ultimately, red spirals force us to reconsider our assumptions about how galaxies evolve. They remind us that the universe doesn't always follow simple rules and that even well-established models can be challenged by unexpected discoveries. Whether they are a brief transitional phase, a sign of slow galactic starvation, or something even stranger, red spirals represent one of the most intriguing puzzles in modern astronomy. And as we continue to explore the cosmos, they may hold the key to unlocking new insights into the very nature of galaxies themselves. The deeper we dig into the mystery of red spirals, the more it becomes clear that they are not just anomalies but key players in the broader story of galaxy evolution. One of the biggest questions still haunting astronomers is whether red spirals are a sign of an incomplete or alternative evolutionary path. Traditionally, the idea has been that spiral galaxies either stay blue and start forming for billions of years or eventually lose their ability to make new stars and morph into elliptical galaxies. But red spirals throw a wrench into that thinking. Instead of neatly transitioning from one form to another, red spirals seem to be stuck in a peculiar in-between state. Some of them appear to be actively fighting against the forces that would typically transform them into ellipticals. Their spiral arms remain intact, defying expectations that they should have become more chaotic and featureless over time. If they are simply on their way to becoming ellipticals, why do we still see them in such large numbers? The sheer persistence of red spirals suggests that they are not just failed ellipticals in the making, but perhaps a distinct and stable class of galaxy that has been overlooked. One possible explanation involves the influence of dark matter. Scientists know that galaxies are surrounded by halos of dark matter, an invisible and mysterious substance that makes up most of the universe's mass. The distribution and density of this dark matter can have profound effects on a galaxy's evolution. Some researchers speculate that red spirals might exist in special dark matter environments that shield them from the gravitational disruptions that usually turn spirals into ellipticals. If this is the case, then red spirals might not be an evolutionary phase at all, but rather a natural outcome of certain dark matter conditions. Another avenue of investigation is the role of external gas flows. Galaxies don't just evolve in isolation, they interact with the cosmic web, a vast network of gas and dark matter filaments that connect galaxies across the universe. Some astronomers believe that red spirals may be caught in regions where the gas supply has been cut off, but not in a way that completely strips them of their structure. Instead of rapidly collapsing into an elliptical shape, these galaxies might be slowly starving over billions of years, their reddish hue a sign of their dwindling fuel reserves. Recent observations from radio telescopes suggest that some red spirals still contain a surprising amount of cold gas, the key ingredient for star formation. But for some reason, they aren't using it efficiently. One theory is that these galaxies have undergone minor interactions with other galaxies that have disrupted their internal processes, making it harder for gas to collapse and form new stars. This would mean that red spirals are not completely dead, they're just inefficient at making stars compared to their blue counterparts. But the biggest mystery remains: what ultimately happens to red spirals? Are they truly stable, or are they just taking an unusually long time to transition into something else? One possibility is that red spirals could eventually reignite their star formation under the right conditions. If they collide with a gas-rich galaxy, for example, they could become blue again, reversing the traditional path of galaxy evolution. There is some evidence that this has happened in certain cases, but it's still unclear how common this process is. Alternatively, red spirals could eventually fade into complete passivity, losing what little remaining star formation they have and becoming even redder over time. In this case, they might ultimately become indistinguishable from elliptical galaxies, but on a much slower timescale than previously thought. This would suggest that the life cycle of galaxies is more complex than a simple transition from spirals to ellipticals, and that multiple evolutionary pathways are possible. As new telescopes and simulations continue to refine our understanding, red spirals stand as a reminder that the universe is far more intricate than our models often assume. They challenge our notions of order and classification, showing us that nature doesn't always follow the patterns we expect. Whatever their true nature, one thing is certain: the mystery of red spirals is far from solved, and they may hold the key to rewriting what we thought we knew about galaxies and the vast, ever-changing cosmos. The deeper astronomers investigate the nature of red spirals, the more the mystery seems to grow rather than shrink. At first glance, these galaxies seem like contradictions, defying the conventional wisdom that spiral galaxies should be rich in star formation, appearing blue due to the hot, young stars within them. Yet, red spirals don't follow this expected pattern. Their structure remains well preserved, with their characteristic arms still visible, yet they lack the intense star formation that defines most other spirals. This inconsistency raises an overwhelming number of questions. If they are in the process of evolving into elliptical galaxies, why do they still retain their spiral structures? If they are merely old spirals that have run out of fuel for star formation, why do some still contain substantial amounts of gas? And if they are not an evolutionary step at all but a separate class of galaxies altogether, why are they so rare compared to their blue counterparts? These are the kinds of questions that have left scientists both frustrated and fascinated as they attempt to unravel the secrets of these cosmic outliers. One of the leading hypotheses about the existence of red spirals is that they are galaxies in the midst of being transformed. Traditionally, the pathway from a spiral to an elliptical galaxy is believed to involve a violent interaction, such as a major galactic collision or a sudden removal of gas due to environmental effects. These interactions are thought to trigger bursts of star formation that eventually burn through all available fuel, leaving behind a red, passive galaxy. However, red spirals don't seem to fit neatly into this narrative. Unlike elliptical galaxies, which have lost all semblance of their former spiral structures, red spirals continue to maintain their elegant, rotating arms. This suggests that whatever process is turning them red isn't powerful enough to completely restructure them. Instead, it seems to be selectively shutting down star formation while leaving the rest of the galaxy's shape intact. One possible mechanism behind this phenomenon is known as strangulation. In this scenario, red spirals might have been cut off from the cosmic gas reservoirs that normally provide fresh material for new stars. This could happen if a galaxy drifts into a dense cluster environment, where the surrounding medium strips away its ability to pull in new gas. Without this external supply, the remaining gas within the galaxy gets used up slowly over billions of years, leading to a gradual decline in star formation. But this explanation raises another puzzle. If red spirals are the result of strangulation, then why do some still contain measurable amounts of gas? Some studies have revealed that a number of red spirals still possess significant reserves of cold hydrogen, the primary ingredient needed to form new stars. If the gas is there, then why is it not being converted into young, hot, blue stars like in other spirals? One answer might lie in the role of the galaxy's internal dynamics. It's possible that the gas in red spirals is too hot, or too spread out to effectively collapse into new stars. Some research suggests that red spirals might have unusually high levels of turbulence within their disks, which could prevent gas from condensing into the dense clouds needed for star formation. Alternatively, their central black holes might be playing a role. Many galaxies contain supermassive black holes at their cores, and when these black holes become active, they can release enormous amounts of energy into their surroundings. This process, known as AGN, active galactic nucleus feedback, can heat up the surrounding gas, making it much harder for it to cool and form new stars. Some red spirals show signs of past AGN activity, suggesting that this mechanism could be responsible for shutting down star formation in at least some cases. But the mystery doesn't stop there. If AGN feedback is responsible for turning spirals red, then why doesn't this happen to all spiral galaxies with active black holes? Some blue spirals also contain powerful AGNs, yet they continue to form stars without issue. This implies that AGN feedback alone is not enough to explain the existence of red spirals. There must be additional factors at play. Some researchers believe that a combination of multiple processes is responsible, with different red spirals undergoing different evolutionary pathways depending on their environment and history. This could explain why red spirals display such a wide variety of properties. Some might have undergone mild interactions with neighboring galaxies that disrupted their star formation processes, while others might be suffering from gradual gas starvation due to their locations in dense cosmic filaments. One of the biggest breakthroughs in understanding red spirals came from large-scale galaxy surveys, such as the Sloan Digital Sky Survey (SDSS). These surveys have allowed astronomers to study red spirals in greater detail than ever before, revealing new clues about their structure, composition, and distribution throughout the universe. One striking finding is that red spirals tend to be more common in certain types of environments. Unlike blue spirals, which are often found in relative isolation, red spirals are more frequently located in intermediate density regions, places that are either completely empty nor as crowded as the centers of massive galaxy clusters. This suggests that environment plays a key role in their formation. Perhaps there are galaxies that have been affected by nearby interactions, but not enough to completely destroy their spiral structure. Or perhaps they have been slowly evolving in these environments for billions of years, gradually changing color without undergoing any dramatic transformations. Another important clue comes from studying the internal structures of red spirals. Some research suggests that these galaxies might have thicker, more stable disks compared to blue spirals, which could make them more resistant to the kinds of disturbances that typically lead to a transition into an elliptical galaxy. If this is the case, then red spirals might not be a temporary phase at all. They could be a stable, long-lived class of galaxy that has simply been overlooked until now. This would fundamentally change our understanding of galaxy evolution, forcing astronomers to rethink the traditional models that describe how galaxies change over time. There's also the question of whether red spirals have always existed in significant numbers, or if they are more common in certain eras of cosmic history. By studying galaxies at different distances, astronomers can effectively look back in time, observing how galaxies appeared billions of years ago. If red spirals were more abundant in the early universe, this could suggest that they are a fading population, slowly disappearing as galaxies either regain their ability to form stars or transition into ellipticals. But if red spirals have existed in roughly the same numbers throughout cosmic history, this would imply that they are not a temporary phase at all, but rather a long-lasting phenomenon. Ultimately, red spirals stand as a testament to the complexity of the universe. They challenge our existing models, forcing us to confront the possibility that galaxy evolution is not as straightforward as we once believed. Their very existence raises fundamental questions about how galaxies grow, change, and interact with their environments. Are they galaxies that are struggling against the inevitable forces of transformation, desperately clinging to their spiral shapes even as their star-forming abilities fade? Or are they something else entirely? An overlooked but important class of galaxy that has been hiding in plain sight all along? With upcoming advances in telescope technology, the future of red spiral research looks brighter than ever. Missions like the James Webb Space Telescope and the Vera C. Rubin Observatory's upcoming surveys will provide an unprecedented level of detail, allowing astronomers to probe deeper into the mysteries of these galaxies. By studying them across different wavelengths of light, scientists hope to uncover new insights into the processes shaping them, revealing whether they are on their way to becoming something else or if they are a stable, long-lived population that has defied classification for far too long. For now, red spirals remain one of the most intriguing enigmas in modern astronomy. They are reminders that the universe doesn't always follow simple rules and that every new discovery has the potential to challenge what we think we know. As research continues, one thing is certain: red spirals are more than just a curiosity. They may hold the key to understanding galaxy evolution in ways we never imagined. The study of red spirals continues to pose more questions than answers, leading to a broader reconsideration of how galaxies evolve and interact with their environments. As astronomers collect more data, they begin to suspect that red spirals might not be a single, uniform group, but rather a collection of galaxies that have reached their current state through different mechanisms. This would mean that what we call red spirals today could actually represent multiple pathways of galactic transformation, each influenced by unique cosmic events. Some may be on their way to becoming elliptical galaxies, while others could remain in their peculiar state indefinitely, defying classification altogether. One of the key aspects of this mystery lies in how red spirals maintain their structure despite the apparent cessation of star formation. In typical galaxy evolution models, spiral arms are thought to be shaped and sustained by the continuous birth of new stars. The fact that red spirals still exhibit defined arms despite their relative lack of young stars suggests that there may be alternative mechanisms keeping their structure intact. One possibility is that the gravitational influence of dark matter plays a larger role than previously thought, stabilizing the disk and preventing it from collapsing into a more amorphous shape. Alternatively, some red spirals may be experiencing very faint, sporadic bursts of star formation that are too subtle to be detected using conventional methods, allowing them to sustain their spiral patterns over long periods of time. Another theory suggests that red spirals may have had their star-forming capabilities disrupted by interactions with other galaxies. In many cases, when galaxies pass close to one another or even merge, their internal gas can be violently stirred up or stripped away entirely. This process, known as ram pressure stripping, is particularly common in galaxy clusters, where the high-speed movement of galaxies through the surrounding hot plasma can strip away their outer gas layers. If a spiral galaxy were to lose just enough gas to prevent widespread star formation while still retaining its overall structure, it could potentially become a red spiral. However, not all red spirals are found in dense galaxy clusters, meaning that this explanation alone cannot account for their existence. Interestingly, some studies have indicated that red spirals tend to have higher than average amounts of dust compared to their blue counterparts. Dust can obscure the light from young stars, making a galaxy appear redder than it actually is. This raises the possibility that at least some red spirals might not be entirely devoid of star formation, but rather, their young stars are being hidden behind thick layers of interstellar dust. If this is the case, then red spirals may not be as fundamentally different from blue spirals as they appear, but rather an observational illusion caused by dust obscuration. Future telescopes capable of peering through dust, such as the James Webb Space Telescope, could help resolve this question by observing red spirals in infrared wavelengths, where dust is less of a hindrance. Another line of inquiry focuses on the role of galactic bulges, the dense, central regions of galaxies that contain older stars and sometimes active supermassive black holes. Red spirals tend to have larger, more prominent bulges compared to blue spirals, leading some astronomers to speculate that their transformation may be linked to the growth of their central regions. If a spiral galaxy undergoes a process that increases the mass of its bulge, such as multiple minor mergers or internal disk instabilities, this could alter the overall balance of the galaxy, potentially suppressing star formation in its outer regions while preserving the spiral arms. This could explain why some red spirals are able to maintain their shape even though they no longer exhibit the same level of star formation as their blue counterparts. Despite all these theories, the fundamental question remains: are red spirals a transitional phase between blue spirals and elliptical galaxies, or are they an entirely separate class of galaxy that has been overlooked until now? The answer to this question could have profound implications for our understanding of galaxy evolution as a whole. If red spirals are a temporary state, then we would expect to see a clear evolutionary pathway linking them to other types of galaxies, with measurable timescales for how long they remain in this phase before transitioning into something else. But if they are a stable, long-term category of galaxies, then this would indicate that our current models of galaxy evolution are missing something fundamental. One of the best ways to answer this question is to look at red spirals across different points in cosmic history. By studying galaxies at varying distances, astronomers can effectively rewind the clock and observe how galaxies appeared in earlier epochs. If red spirals were more common in the distant past, this could suggest that they are a transient phase, slowly fading away as galaxies evolve. But if they exist in roughly the same numbers throughout cosmic history, this would imply that they are a persistent feature of the universe, existing in parallel with blue spirals and elliptical galaxies rather than serving as an intermediate step between them. Adding to the puzzle, recent observations suggest that some red spirals may have the potential to reignite their star formation under the right conditions. If a red spiral were to encounter a fresh supply of gas, such as through a minor merger with a gas-rich dwarf galaxy or by drifting back into a region with abundant intergalactic material, it could theoretically resume forming new stars, transitioning back into a blue spiral. This would indicate that red spirals are not necessarily in a one-way path toward becoming ellipticals, but rather that their fate is highly dependent on their environment and interactions with other galaxies. One of the most compelling aspects of the red spiral mystery is that it forces astronomers to reconsider the entire framework of how galaxies evolve. Traditional models often assume a straightforward path: young, gas-rich spirals gradually consume their fuel and either transform into lenticular or elliptical galaxies as they age, or they merge with other galaxies and form new structures. But red spirals disrupt this narrative, suggesting that galaxy evolution may be more complex than a simple linear progression. Instead, galaxies may follow multiple pathways, with some capable of switching between different states depending on external influences. As new observational data continues to pour in, astronomers are beginning to explore even more unconventional explanations for red spirals. Some have proposed that exotic astrophysical processes, such as interactions with dark matter halos or large-scale magnetic fields, might be playing a role in shaping these galaxies. Others suggest that red spirals could be the remnants of ancient cosmic events that took place billions of years ago, their properties reflecting the conditions of the early universe rather than more recent interactions. What makes red spirals so intriguing is that they represent a rare challenge to our current understanding of the cosmos. They are an example of how even the most well-established scientific theories can be questioned by new discoveries, reminding us that the universe is far more complex and unpredictable than we often assume. Every time astronomers think they have a handle on how galaxies behave, anomalies like red spirals emerge to prove them wrong. And perhaps that is the greatest mystery of all, not just why these galaxies exist, but what their existence tells us about the limitations of our knowledge. The more we study red spirals, the clearer it becomes that they hold critical clues about the forces shaping the universe. Whether they are a fleeting stage in a galaxy's life cycle or an overlooked category of galaxy in their own right, red spirals have forced astronomers to reconsider some of the most fundamental assumptions about how galaxies change over time. As new telescopes and simulations push the boundaries of what we can observe, the answers may finally come into focus. But until then, red spirals remain one of the great cosmic enigmas. The mystery of red spirals is not just about their existence, but about what they reveal regarding the deeper, hidden mechanisms of galaxy evolution. They defy conventional classification because they blur the line between two well-understood galaxy types, blue spirals and red ellipticals. If the transition from one to the other were as simple as running out of star-forming gas, we would expect red spirals to be a brief, transient phase. But their persistence and widespread presence challenge that idea, suggesting a more complex process at work. One of the most perplexing aspects of red spirals is the sheer variety among them. Some red spirals show clear signs of past interactions, tidal tails, distorted disks, or even faint remnants of merged companions, while others appear almost pristine, as if they have never undergone significant galactic collisions. This diversity suggests that different evolutionary paths may lead to the same final result, a spiral galaxy that has become red but has somehow avoided becoming elliptical. The fact that red spirals are found in both isolated regions and galaxy clusters adds another layer of confusion. If external influences were the primary cause, we would expect red spirals to be clustered in specific environments, yet they appear across different cosmic settings. The role of supermassive black holes in the centers of red spirals is another avenue of investigation. Many of these galaxies host active galactic nuclei, AGN, which are powered by matter falling into the central black hole. AGN activity can generate powerful jets and outflows that heat or expel gas, shutting down star formation in the surrounding galaxy. If an AGN turned on at just the right moment, it could theoretically halt star formation in a blue spiral before it had a chance to morph into an elliptical. This would create a red spiral that retains its structure but lacks young stars. However, this explanation does not fit all cases. Some red spirals do not show evidence of strong AGN activity, while others have AGN that are too weak to significantly impact star formation. One of the key factors that distinguishes red spirals from elliptical galaxies is their angular momentum. Spiral galaxies are dominated by rotation. Their stars, gas, and dust all orbit the galactic center in an organized, disk-like fashion. Ellipticals, on the other hand, are dominated by random stellar motions, which give them their rounder, more amorphous shape. If red spirals truly were an intermediate stage between spirals and ellipticals, we would expect to see signs of their rotation slowing down over time. However, observations suggest that many red spirals retain significant angular momentum, meaning they are not following the expected path toward becoming ellipticals. This raises the possibility that red spirals may be a long-lived state rather than a transitional phase. Another factor complicating the mystery is the unusual star populations found in red spirals. While their overall light is dominated by older, redder stars, some still show evidence of faint, residual star formation. In some cases, this star formation is concentrated in specific regions, such as in a central ring, along the edges of spiral arms, or even in isolated star-forming pockets scattered throughout the disk. This suggests that the gas within these galaxies is not entirely depleted, but is somehow being prevented from forming stars at a normal rate. It could be that turbulence, magnetic fields, or even exotic processes related to dark matter are interfering with the formation of new stars. The connection between red spirals and their dark matter halos is another avenue that astronomers are exploring. Every galaxy is embedded in a vast, invisible halo of dark matter that provides the gravitational framework for its structure. Some studies have suggested that red spirals tend to have denser or more extended dark matter halos compared to blue spirals of similar size. If this is true, then the interaction between the visible matter and dark matter could be influencing the way these galaxies evolve. A denser dark matter halo might prevent gas from collapsing efficiently into star-forming regions, or it could create subtle gravitational effects that disrupt the normal cycle of gas inflows and outflows. One of the biggest questions surrounding red spirals is whether they can be rejuvenated. If a red spiral were to encounter a fresh supply of cold gas, perhaps through a minor merger with a gas-rich dwarf galaxy or by passing through a dense intergalactic filament, it could, in theory, restart its star formation and transition back into a blue spiral. There is some observational evidence to suggest that this happens in certain cases, but it is unclear how common this process is. If red spirals can switch back and forth between active and inactive star formation, then they may represent a more dynamic and flexible stage in galaxy evolution than previously thought. The observational challenges associated with red spirals add another layer of difficulty to the puzzle. Many of these galaxies are relatively faint, making it difficult to obtain detailed spectroscopic data that would reveal the precise composition and motion of their stars and gas. Additionally, dust obscuration can make it hard to determine whether a galaxy is truly red due to a lack of young stars or simply because its blue light is being absorbed by interstellar dust. Future telescopes, such as the James Webb Space Telescope and next-generation radio observatories, may provide the tools needed to see through this cosmic haze and uncover the hidden details of red spirals. Despite the many unknowns, one thing is certain: red spirals challenge our understanding of how galaxies form, evolve, and interact with their surroundings. They suggest that the standard models of galaxy evolution may be too simplistic and that there are multiple, overlapping pathways that galaxies can take as they age. Whether red spirals are a stepping stone between blue spirals and ellipticals, a relic of past galactic interactions, or a completely separate category of galaxy, they remind us that the universe is far more complex than we often assume. The ongoing study of red spirals is not just about solving a single mystery, but about refining our broader understanding of the cosmos. Every time astronomers think they have pieced together the big picture, objects like red spirals emerge to challenge those assumptions. This is the nature of science. Each discovery leads to new questions, and each unanswered question pushes us to develop new theories, new technologies, and new ways of thinking about the universe. As we continue to explore deeper into the cosmos, the mystery of red spirals may one day be solved. But until then, they remain a striking reminder that even the most fundamental aspects of the universe, such as the way galaxies evolve, can still hold surprises. Perhaps the most exciting possibility is that the answer to the red spiral mystery will not only explain their existence, but also lead to new insights into the nature of dark matter, galaxy formation, and even the very structure of the universe itself. The mystery of red spirals is a perfect example of how the universe refuses to fit into neat, predictable patterns. These galaxies sit at the crossroads of classification, blending characteristics from two well-defined groups, spirals and ellipticals, while breaking the expected evolutionary path. They challenge our models of galaxy formation, hinting that the processes shaping the universe may be more intricate and interconnected than we once thought. But what exactly led to the formation of red spirals? Why do they exist in such a liminal state, and what does their presence tell us about the nature of galaxies, star formation, and even the fundamental forces shaping the cosmos? One of the leading hypotheses surrounding red spirals is that they result from an unusual form of quenching, an abrupt halt in star formation that does not follow the typical patterns we see in other galaxies. In most cases, galaxies stop forming stars when they lose their supply of cold gas, either by expelling it through supernova feedback, exhausting it over billions of years, or having it stripped away by external forces such as interactions with other galaxies. However, red spirals seem to have gone through this quenching process while still retaining their spiral structure. This is unusual because, typically, when a galaxy loses its ability to form new stars, it also undergoes a transformation in shape, gradually morphing into a more featureless elliptical galaxy due to internal and external gravitational forces. This suggests that red spirals are somehow retaining their structural integrity while simultaneously losing their star-forming capacity. There are several possible explanations for this. One idea is that red spirals are simply old, isolated galaxies that have consumed all their available gas but have not yet merged with another galaxy or undergone a transformation into an elliptical. If this were the case, we might expect red spirals to be more common in low-density environments, where galaxy interactions are rare. However, red spirals are also found in galaxy clusters, where interactions are frequent, making this explanation incomplete. Another possibility is that red spirals are being affected by an external mechanism that removes their star-forming gas without significantly disrupting their structure. One such process is known as strangulation, where a galaxy loses its ability to replenish its gas supply over time. This can happen when a galaxy is embedded in a hot intergalactic medium, such as in a dense galaxy cluster, where the surrounding environment prevents fresh gas from cooling and falling into the galaxy. Over time, the galaxy depletes its existing gas through star formation, but because it cannot replenish its supply, it gradually runs out of material to form new stars, leading to its red color. Another, more dramatic possibility is that some red spirals have undergone a process called ram pressure stripping. This occurs when a galaxy moves at high speed through a dense intergalactic medium, such as the hot plasma that fills galaxy clusters. The pressure exerted by this medium can strip away the galaxy's gas, much like wind blowing leaves off a tree. If a spiral galaxy experiences ram pressure stripping, it could lose its star-forming gas relatively quickly while still maintaining its spiral structure for a significant period before eventually evolving into an elliptical. However, the presence of red spirals in isolated environments challenges this explanation as well. Not all red spirals reside in galaxy clusters where ram pressure stripping could be at play. Some exist in relatively empty regions of space, far from the gravitational influence of other galaxies. This suggests that other factors, such as internal processes or hidden astrophysical forces, must also be contributing to their formation. One intriguing possibility is that dark matter may play a role in the existence of red spirals. Every galaxy is surrounded by a massive halo of dark matter, an invisible form of matter that does not emit or absorb light but exerts gravitational influence. Studies have suggested that red spirals tend to have unusually dense dark matter halos compared to their blue counterparts. If dark matter influences the motion of gas within galaxies, it could be preventing new star formation in red spirals by keeping gas in a highly turbulent state, preventing it from collapsing into star-forming regions. Alternatively, dense dark matter halos might alter the way a galaxy interacts with its surroundings, making it more susceptible to environmental quenching processes. The relationship between red spirals and their central supermassive black holes is another area of intense research. Most large galaxies harbor a supermassive black hole at their core, and these black holes can have profound effects on their host galaxies. When a black hole is actively feeding on surrounding matter, it releases enormous amounts of energy in the form of radiation, jets, and winds, an effect known as active galactic nucleus (AGN) feedback. This energy can heat or expel gas within the galaxy, effectively shutting down star formation. Many red spirals show signs of past AGN activity, suggesting that their central black holes may have played a role in quenching their star formation. However, this explanation does not hold for all red spirals, as some lack strong AGN signatures, indicating that multiple mechanisms may be at play. There is also the possibility that red spirals are the remnants of past galactic interactions that have disrupted their ability to form new stars without destroying their structure. In this scenario, a red spiral may have undergone a minor merger with another galaxy, leading to turbulence and gas depletion that halted star formation while leaving the spiral arms intact. Alternatively, gravitational interactions with nearby galaxies could have disrupted gas flow patterns, preventing fresh gas from accumulating in star-forming regions. Adding to the complexity, some red spirals show faint signs of ongoing star formation in specific regions, such as in a central ring or along the edges of their spiral arms. This suggests that while star formation has largely been suppressed, it has not been entirely shut down. In some cases, these galaxies may still possess small pockets of star-forming gas that are gradually being consumed, leading to a slow and uneven transition to a fully quiescent state. The presence of these localized star-forming regions indicates that the quenching process in red spirals is not always uniform and may be influenced by a variety of local conditions. The mystery deepens when we consider the possibility of rejuvenation, a process where a red spiral could regain its ability to form stars under the right circumstances. If a red spiral were to encounter a fresh supply of cold gas, such as through a minor merger with a gas-rich dwarf galaxy or by accreting intergalactic material, it could theoretically restart its star formation and transition back into a blue spiral. There is some evidence that this occurs in certain cases, as some red spirals show signs of recent gas accretion. However, the frequency and conditions required for this rejuvenation remain unclear. Ultimately, the existence of red spirals challenges the traditional, linear model of galaxy evolution. Instead of galaxies following a strict path from blue spirals to red ellipticals, red spirals suggest that there may be alternative evolutionary routes, loops, or even prolonged states of equilibrium that allow galaxies to exist in an unexpected form for billions of years. Their presence hints that galaxy evolution is not a simple process of aging and transformation, but rather a dynamic interplay of internal and external forces that can create surprising and counterintuitive outcomes. As astronomical technology continues to advance, future telescopes and observational techniques may finally unravel the mystery of red spirals. Instruments like the James Webb Space Telescope, the upcoming Vera C. Rubin Observatory, and next-generation radio telescopes will provide unprecedented views of these enigmatic galaxies, allowing astronomers to analyze their structure, motion, and chemical composition in greater detail than ever before. These observations may reveal whether red spirals are a rare, transient phenomenon, or a common and long-lasting phase in galactic evolution. Until then, red spirals remain a fascinating anomaly, an unexpected deviation from the patterns we thought we understood about the universe. Their existence reminds us that the cosmos is full of surprises, and that even something as seemingly well-mapped as galaxy evolution can still hold deep and unresolved mysteries. Each new discovery about these galaxies not only helps us understand them better but also forces us to rethink our assumptions about how the universe works. The fact that red spirals exist at all raises deep questions about the assumptions we make in astrophysics. For decades, the standard model of galaxy evolution suggested a fairly straightforward progression. Young, gas-rich spiral galaxies form new stars at a rapid rate, giving them their characteristic blue color. Over billions of years, they either merge with other galaxies or undergo internal processes that strip away or heat up their gas, eventually quenching star formation and transforming them into red, elliptical galaxies. But red spirals do not fit neatly into this sequence. Instead, they appear to be stuck in a transitional state, either fully active nor entirely passive, defying the expected pathways of galaxy evolution. One possible explanation for this unexpected existence lies in the role of environment. The environment a galaxy resides in can have a profound impact on its evolution, influencing everything from its shape to its ability to form stars. In high-density regions, such as galaxy clusters, galaxies are subjected to extreme gravitational forces, interactions, and processes that can strip them of their star-forming gas. Yet, red spirals are found in a variety of environments, from dense clusters to relatively isolated regions of space. This suggests that multiple factors, rather than a single cause, contribute to their unusual state. One such factor is galaxy mergers. When two galaxies collide, their gas, stars, and dark matter interact in complex ways, triggering bursts of star formation while simultaneously redistributing gas throughout the system. In some cases, this can result in the rapid consumption of star-forming gas, leading to a premature halt in star formation, while the galaxy's spiral structure remains intact. If a spiral galaxy undergoes a merger with a smaller, gas-poor galaxy, it could deplete its remaining gas without disrupting its overall shape, creating a red spiral. Another environmental process that could contribute to the existence of red spirals is harassment, repeated gravitational interactions with neighboring galaxies. These encounters can stir up turbulence within a galaxy, preventing gas from cooling and collapsing into new stars. While not as dramatic as a full merger, prolonged harassment over millions or billions of years could gradually suppress star formation in a spiral galaxy, leading to a red spiral. Further complicating the picture is the role of cosmic filaments, vast, thread-like structures of galaxies and dark matter that form the backbone of the cosmic web. Galaxies residing within or near these filaments may experience different rates of gas accretion, with some galaxies being cut off from fresh supplies of star-forming material, while others continue to draw in gas. If red spirals are preferentially located in regions where gas inflow is suppressed, this could explain why they appear to be stalled in an intermediate state. Observations also suggest that red spirals tend to have older stellar populations compared to their blue counterparts. This indicates that their transition from blue to red occurred gradually, rather than as a sudden event. Unlike post-starburst galaxies, which show clear evidence of having undergone a recent and dramatic shutdown of star formation, red spirals seem to have faded more slowly over time. This gradual quenching could be the result of a slow depletion of gas reserves rather than an external event cutting off star formation abruptly. A particularly intriguing aspect of red spirals is that their spiral arms often remain well-defined, despite their lack of new star formation. In typical spiral galaxies, star formation plays a crucial role in maintaining the structure of spiral arms. The birth of new stars creates pressure waves that reinforce the spiral pattern, keeping it from fading over time. In red spirals, however, this mechanism is no longer active, yet the arms persist. This suggests that other forces, such as the gravitational influence of dark matter or the internal dynamics of the galaxy, may be helping to preserve the spiral structure long after star formation has ceased. Another key question is whether red spirals represent a temporary phase in galaxy evolution or a more stable, long-lasting state. If they are merely galaxies in transition, we would expect them to eventually evolve into more traditional red ellipticals. However, some red spirals appear to have maintained their structure for billions of years, suggesting that they may represent a unique and stable category of galaxies rather than a fleeting phase. This raises an even deeper question. Could there be entire populations of galaxies that exist outside our current classification systems? Astronomers have long categorized galaxies into broad types: spirals, ellipticals, lenticulars, based on their appearance and star-forming activity. But red spirals hint at the possibility that these categories may be too simplistic, and that galaxy evolution is far more diverse and nonlinear than previously thought. If red spirals are indeed a distinct class of galaxies, it would force astronomers to rethink fundamental assumptions about how galaxies change over time. It might also suggest that there are other, yet-to-be-discovered forms of galactic evolution that do not conform to existing models. The discovery of red spirals has already prompted new theoretical work in astrophysics, leading scientists to explore alternative pathways for how galaxies age, interact, and evolve. The question of how common red spirals are is also an important one. Are they a rare anomaly, or is their presence more widespread than we realize? Recent surveys, such as those conducted by the Sloan Digital Sky Survey (SDSS), have identified thousands of red spirals, suggesting that they are not merely an oddity but a significant component of the galaxy population. However, their true prevalence is still uncertain, as they are more difficult to detect than traditional blue spirals or red ellipticals. Many red spirals have relatively low surface brightness, meaning that they are faint and harder to distinguish in deep sky surveys. This raises the possibility that there are many more red spirals waiting to be discovered, hiding in the depths of the cosmos. Future telescopes and observational campaigns will play a crucial role in unraveling this mystery. Instruments such as the James Webb Space Telescope, JWST, and the upcoming European Extremely Large Telescope, ELT, will allow astronomers to study red spirals in unprecedented detail, examining their chemical composition, internal dynamics, and dark matter distribution. These observations may provide the missing pieces needed to finally explain why red spirals exist and what their presence tells us about the broader history of galaxy formation. One of the most exciting possibilities is that red spirals may help bridge the gap between different types of galaxies, serving as a key piece of evidence in understanding how galaxies transition from one form to another. If we can determine the exact mechanisms that cause spiral galaxies to turn red without losing their structure, we may gain new insights into the forces shaping the universe at large. But even as we gather more data, the mystery of red spirals remains one of the most perplexing puzzles in modern astrophysics. Their existence challenges long-held beliefs, forces us to reconsider how galaxies evolve, and hints at the complexity of the universe in ways we are only beginning to grasp. For now, red spirals stand as a cosmic paradox, a reminder that the universe is far from predictable, and that every new discovery brings with it more questions than answers. The mystery of red spirals forces us to confront the gaps in our understanding of galaxy evolution. For decades, astronomers have relied on the standard model of cosmology to explain how galaxies form, evolve, and eventually see star formation. This model has been incredibly successful in explaining many of the large-scale structures we see in the universe today. Yet, red spirals seem to exist outside of this neat framework, suggesting that there are processes at play that we do not fully understand. Could they be the remnants of an ancient population of galaxies that evolved differently from the rest? Or are they still undergoing transformations that challenge the traditional definitions of galactic life cycles? One of the most perplexing aspects of red spirals is their distribution in the universe. Studies have found that they appear in both dense galactic clusters and more isolated environments, suggesting that a single explanation, such as interactions with neighboring galaxies, may not be enough to account for their formation. If interactions with other galaxies were the primary cause, we would expect red spirals to be far more common in dense environments where gravitational interactions are frequent. However, their presence in less populated regions suggests that internal processes, such as the exhaustion of star-forming material or the effects of dark matter, might be just as important. Dark matter could play a crucial role in maintaining the structure of red spirals. In traditional spiral galaxies, the gravitational influence of dark matter helps sustain the rotation of the galaxy and provides a framework around which gas and stars are arranged. But what happens when a galaxy runs out of cold gas to form new stars? If the dark matter halo remains intact, it could help preserve the spiral arms long after active star formation has ceased. This might explain why red spirals retain their structure even after becoming inactive in terms of star production. Another intriguing possibility is that red spirals are the result of a slow, internal strangulation process. In this scenario, a galaxy may gradually lose its ability to pull in fresh gas from its surroundings, either due to the influence of its dark matter halo or the depletion of available gas in its local environment. Without new material to fuel star formation, the galaxy would slowly transition from blue to red as its existing stars age and cool. This process could take billions of years, making red spirals a long-lived but ultimately temporary stage in a galaxy's life. But why do some spirals remain blue while others turn red? One factor may be the initial mass of the galaxy. Larger, more massive galaxies may be better at retaining their gas supplies and resisting the effects of external influences. Smaller galaxies, on the other hand, may lose their gas more easily due to interactions with the intergalactic medium or their own internal feedback mechanisms. If red spirals tend to be of a certain mass range, this could provide a clue as to why they exist and how they fit into the broader picture of galaxy evolution. Another key question is whether red spirals represent a dead end in galaxy evolution or if they can be revived under the right conditions. In theory, if a red spiral were to encounter a fresh supply of gas, perhaps by merging with a smaller, gas-rich galaxy, it could reignite star formation and become blue once again. Observations of some red spirals suggest that weak star formation is still occurring in certain regions, indicating that they may not be entirely dormant. If future studies confirm that red spirals can transition back into active, star-forming galaxies, it would add yet another layer of complexity to our understanding of galactic evolution. There is also the question of whether red spirals exist in the early universe or if they are a more recent phenomenon. If red spirals are found at high redshifts, meaning they existed when the universe was much younger, it would suggest that they represent an ancient and fundamental aspect of galaxy formation. On the other hand, if they are only found in the more recent cosmic past, it could indicate that they are the product of more modern galactic interactions. Current observations are limited by the capabilities of existing telescopes, but future missions such as the James Webb Space Telescope, JWST, may help provide answers by looking further back in time than ever before. Red spirals also challenge our understanding of how galaxies interact with their surroundings. Traditional models suggest that galaxies in dense environments should experience more rapid transformations due to interactions with neighboring galaxies and the hot gas of galaxy clusters. Yet, some red spirals appear to have remained isolated for billions of years, suggesting that internal processes, rather than external forces, may be the dominant factor in their evolution. If this is the case, it could mean that many galaxies undergo changes that are not directly influenced by their surroundings, raising new questions about the role of environment in galactic life cycles. Furthermore, the existence of red spirals may have implications for the study of cosmic evolution as a whole. If they are more common than previously thought, it could mean that our understanding of how galaxies age and die is incomplete. It might also suggest that there are other types of galaxies that do not fit neatly into our current classification system. For example, are there intermediate forms between blue spirals, red spirals, and fully elliptical galaxies that we have yet to identify? Could there be other, even rarer types of galaxies that challenge our assumptions about how the universe works? As technology advances and our ability to study the universe improves, we may eventually uncover the full story of red spirals. Future telescopes equipped with more powerful imaging and spectroscopic capabilities will allow us to study these galaxies in greater detail, measuring their chemical compositions, dark matter distributions, and histories of star formation. These observations could reveal new insights into the processes that drive galaxy evolution and help us understand where red spirals fit into the larger cosmic puzzle. For now, red spirals remain an enigma, an anomaly that refuses to be neatly categorized. Their very existence forces astronomers to reconsider long-held beliefs and search for new explanations. Are they relics of an ancient cosmic era, or are they still evolving in ways we do not yet understand? Do they represent a stable, long-lived population of galaxies, or are they merely a transient phase on the way to something else? The answers to these questions could reshape our understanding of the universe and challenge some of the most fundamental principles of astrophysics. As we continue to probe the depths of space, one thing is certain: the discovery of red spirals is a reminder that the cosmos is far more complex and mysterious than we ever imagined. Just when we think we have a clear understanding of how galaxies evolve, a new puzzle emerges, forcing us to rethink everything we thought we knew. Red spirals are not just a curiosity, they are a window into the hidden forces shaping the universe, and unlocking their secrets may lead to some of the most profound discoveries in the history of astronomy. The search for answers about red spirals leads us to an even deeper question: how do we truly define a galaxy's life cycle? For decades, the Standard Model has categorized galaxies based on a relatively linear path. Spiral galaxies are active and full of young stars, elliptical galaxies are old and mostly inactive, and lenticular galaxies represent a kind of middle ground. But red spirals don't fit this model. They have the structure of an active galaxy but the characteristics of a dead one. This contradiction suggests that the way we classify galaxies might be too simplistic. One of the most intriguing possibilities is that red spirals represent an unknown transition state. Galaxies are not static objects. They are constantly evolving, shaped by both internal and external forces. Could red spirals be in the middle of a transformation that we have yet to fully understand? Perhaps they are blue spirals in the process of shutting down their star formation but have not yet become fully elliptical. If this is the case, we might be witnessing a crucial, previously overlooked step in galaxy evolution. To determine what's happening inside red spirals, astronomers use spectroscopy, a technique that allows them to analyze the light coming from a galaxy to determine its chemical composition, temperature, and motion. Spectroscopic studies of red spirals have revealed some surprising results. Unlike elliptical galaxies, which are often filled with old, slow-moving stars, Red spirals contain stars that are still moving in a disk-like pattern, similar to those in normal spiral galaxies. This suggests that whatever process is stopping star formation in red spirals is not destroying their structure, at least not immediately. One major clue comes from the distribution of gas in red spirals. Hydrogen gas, the raw material for star formation, is often scarce in these galaxies, suggesting that something has either stripped it away or prevented it from accumulating. One possible explanation is that red spirals were once normal, blue spirals that lost their gas through interactions with the hot plasma found in galaxy clusters. This process, known as ram pressure stripping, occurs when a galaxy moves through a dense region of intergalactic gas. The pressure from this gas can sweep away the galaxy's own supply of star-forming material, effectively shutting down star formation and causing the galaxy to turn red. However, not all red spirals are found in dense environments. Some exist in relative isolation, where ram pressure stripping is unlikely to occur. This suggests that other mechanisms might be at work. One possibility is that red spirals are victims of internal processes, such as feedback from supermassive black holes at their centers. When a black hole becomes active, it can release powerful jets of energy that heat up or blow away the surrounding gas, preventing it from cooling and forming new stars. If red spirals are home to particularly energetic black holes, this could explain why they have stopped forming stars while retaining their spiral structure. Another intriguing theory is that red spirals are simply running out of fuel due to a phenomenon known as strangulation. Unlike ram pressure stripping, which violently removes gas, strangulation is a slow process in which a galaxy gradually stops pulling in fresh material from its surroundings. Over billions of years, this slow starvation could cause a galaxy to transition from blue to red without undergoing any dramatic structural changes. If strangulation is a common fate for spiral galaxies, red spirals may provide a glimpse into the future of many galaxies, including our own Milky Way. The mystery of red spirals also raises fundamental questions about dark matter. Dark matter is thought to play a crucial role in galaxy formation, providing the gravitational scaffolding that holds galaxies together. If red spirals have different dark matter distributions than other galaxies, this could influence how they evolve. Some studies suggest that red spirals have more concentrated dark matter halos than their blue counterparts, which could make them more resistant to external disturbances. If true, this might explain why red spirals can retain their structure even after shutting down star formation. There's also the question of whether red spirals are more common in certain eras of cosmic history. Are we seeing them more frequently now because they are a late-stage phenomenon, or have they always existed in similar numbers? The answer could provide important clues about the long-term evolution of galaxies. Future telescopes like the James Webb Space Telescope, JWST, and the Vera C. Rubin Observatory will allow astronomers to look deeper into the past, potentially revealing whether red spirals were more or less common in earlier epochs of the universe. Understanding red spirals is not just about solving a single mystery, it's about refining our understanding of how the universe works. Every unexpected discovery forces us to reconsider the assumptions we have made about cosmic evolution. The existence of red spirals suggests that galaxies can take unexpected evolutionary paths, challenging the idea that all spirals are destined to become elliptical galaxies over time. It also hints at the possibility that there are even more undiscovered types of galaxies that do not fit neatly into our current classifications. As astronomers continue to study these enigmatic objects, new technologies and observational techniques will provide deeper insights into their nature. Large-scale galaxy surveys, such as those conducted by the Sloan Digital Sky Survey (SDSS), have already helped identify thousands of red spirals, allowing researchers to analyze them in statistical detail. In the future, high-resolution imaging and advanced simulations may help unravel the forces shaping these galaxies and determine whether they are a fleeting anomaly or a fundamental aspect of galactic evolution. For now, red spirals remain a cosmic puzzle, a category of galaxies that defy easy explanation. Their very existence is a reminder that the universe is far more complex than we often assume. Whether they are relics of a bygone era, transitional objects in the process of becoming something else, or a stable but misunderstood class of galaxies, red spirals challenge us to keep pushing the boundaries of our knowledge. Each new discovery brings us closer to understanding the vast, intricate tapestry of the cosmos. But as red spirals show, the universe is still full of surprises. Red spirals force us to rethink not only the evolution of galaxies but also the very nature of how the universe organizes itself. For decades, astronomers have relied on broad classifications, spirals, ellipticals, irregulars, to sort the vast array of galaxies in the cosmos. But red spirals do not fit neatly into any of these categories. They are structured like young, star-forming galaxies but behave like old, passive ones. Their existence challenges the traditional models that suggest spiral galaxies should remain blue until they transform into elliptical galaxies. This means we may have been oversimplifying galaxy evolution, assuming a rigid pathway when the truth may be far more dynamic and unpredictable. One of the most puzzling aspects of red spirals is the way their stars move. Spiral galaxies typically have a well-defined rotational motion, with stars following organized orbits around the galactic center. Elliptical galaxies, on the other hand, tend to have more chaotic, random stellar motions. What makes red spirals fascinating is that, despite having old, red stars like ellipticals, their stars continue to move in a structured, spiral-like orbit. This suggests that whatever process shut down their star formation did not disrupt their overall structure. Could this mean that star formation and galactic structure are more independent than previously thought? If so, it would challenge long-held assumptions about how galaxies evolve. Another factor to consider is the role of galaxy interactions. The universe is a violent place, and galaxies frequently interact, merge, and collide. These encounters can strip galaxies of their gas, trigger new bursts of star formation, or even reshape them entirely. Some red spirals appear to be in isolated regions of space, while others are found in galaxy clusters where interactions are more common. This raises a crucial question: are red spirals primarily the result of external influences like mergers and stripping, or do they form naturally as part of an internal evolutionary process? If the former is true, then different types of interactions could create different kinds of red spirals, which would explain why some have more gas than others. There's also the question of whether red spirals are simply a temporary phase. Could they eventually lose their spiral arms and become ellipticals, or will they remain in their current state indefinitely? If red spirals are part of a transitional process, then studying them might allow us to predict the future of other galaxies, including the Milky Way. Our own galaxy is currently a blue spiral, actively forming stars. But in a few billion years, it will collide with the Andromeda Galaxy, an event that will reshape both galaxies. Could the Milky Way become a red spiral in the aftermath of this collision before settling into an elliptical shape? If red spirals are a middle stage in galaxy evolution, then they may be a glimpse into our own future. One possible explanation for red spirals that has gained traction in recent years is the idea that they are quenched spirals, galaxies that once formed stars but had their star formation abruptly shut down. This quenching process could be caused by several mechanisms, including interactions with the environment, feedback from supermassive black holes, or even the exhaustion of available gas. But why do some spirals quench while others continue forming stars? This remains one of the biggest unanswered questions in astrophysics. The role of supermassive black holes in shaping red spirals is particularly intriguing. Every large galaxy is thought to host a supermassive black hole at its center. When these black holes become active, they can release enormous amounts of energy, heating up or expelling gas and preventing new stars from forming. Some red spirals exhibit signs of past or ongoing activity from their central black holes, which suggests that this process may have played a role in shutting down their star formation. However, not all red spirals show evidence of such activity, meaning that multiple factors might be at play. One of the most exciting developments in recent years has been the discovery of red spirals in deep space surveys conducted by telescopes like Hubble and the Sloan Digital Sky Survey (SDSS). These surveys have revealed that red spirals are not as rare as once thought. In fact, they appear to make up a significant fraction of all spiral galaxies, especially in certain environments. This suggests that whatever process creates red spirals is more common than previously assumed. If red spirals are a major population of galaxies, then understanding them is crucial for developing a complete picture of cosmic evolution. The existence of red spirals may also have implications for dark matter, the mysterious, invisible substance that makes up most of the universe's mass. Dark matter plays a crucial role in galaxy formation, influencing how galaxies rotate and interact. Some studies suggest that red spirals have more concentrated dark matter halos than their blue counterparts, which could help explain why they retain their structure despite having lost their ability to form new stars. If this is true, it could mean that dark matter influences not just the shape of galaxies, but also their evolutionary pathways. Another lingering mystery is whether red spirals are more common in certain epochs of cosmic history. Were they more abundant in the early universe, or are they a relatively recent phenomenon? If astronomers can determine when red spirals were most prevalent, it could provide important clues about how galaxies evolve over time. Future telescopes, such as the Vera C. Rubin Observatory and the James Webb Space Telescope, will allow astronomers to peer even deeper into the cosmos, potentially revealing new insights about the history of red spirals. Despite all these discoveries, red spirals remain one of the great unsolved mysteries of modern astrophysics. They challenge our understanding of how galaxies form, evolve, and die. They force us to reconsider the role of external forces, internal processes, and even dark matter in shaping the universe. Each new study brings us closer to an answer, but also raises new questions. What ultimately causes a spiral galaxy to stop forming stars? How long can a red spiral maintain its structure before transforming into something else? And what do red spirals tell us about the fate of our own galaxy? The more we study red spirals, the more we realize how little we truly understand about the cosmos. They are a reminder that the universe is still full of surprises, waiting to be uncovered. With each new observation, we inch closer to unraveling one of the greatest astronomical puzzles of our time. But for now, red spirals remain an enigma, beautiful, mysterious, and defiant in their refusal to fit neatly into our existing models of the universe. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.